Right now, at this exact moment, there is a place in your solar system where the temperature has not risen above -230 degrees Celsius in 4.5 billion years. Not for a single day, not for a single hour, not for a single second since before the first living cell divided on the surface of the young Earth. 4.5 billion years of unbroken cold. The sunlight that reaches this place carries roughly 1/1600th the energy it delivers to your skin on a warm afternoon. If you stood there and looked up, the sun would still be the brightest object in the sky, but it would no longer be a disk. It would be a point, a sharp, brilliant, unwavering point of light, indistinguishable in apparent size from the stars surrounding it. The star that fills your sky, that warms your face, that drives every weather system and ocean current and biological process on your world, would be reduced to something you could cover with the tip of a pin held at arm's length. It would still outshine everything else, but it would no longer feel like yours. This place is not in another galaxy. It is not in another star system. It is not even in the theoretical outer boundaries of the cosmos. It is part of your solar system. It orbits the same star that rises over your horizon every morning. It formed from the same cloud of gas and dust that built the ground beneath your feet. It is connected to your world by the same gravity, the same physics, the same unbroken chain of cause and effect stretching back to the birth of everything. And almost no one knows it is there. Not truly. Not in any way that matches the reality. Most people carry a picture of the solar system that was handed to them in childhood, a bright yellow sun at the center, 8 planets arranged in a neat procession, each one labeled, each one photographed, each one assigned a place in a sequence that feels complete. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, maybe Pluto at the end, depending on which version of the story you were taught. The planets grow larger, then smaller again. The gaps between them widen. And then, after Neptune, the picture simply stops. White space, the edge of the page, the implicit message that there is nothing more worth drawing. That picture is not wrong. Every object in it is real. Every distance, when adjusted for the compression necessary to fit a diagram on a page, reflects something true about the structure of the inner solar system. But it is incomplete in a way that fundamentally distorts your understanding of where you live. The picture stops at Neptune. The solar system does not. Beyond Neptune, stretching outward for billions of miles in every direction, lies a region so vast, so cold, so structurally complex, and so scientifically significant that its existence forces a complete revision of everything that diagram implied. Scientists call it the Kuiper Belt, and what it reveals about the true architecture of your cosmic home is not a footnote to the familiar story of 8 planets orbiting a star. It is a correction to the story's most basic assumption, the assumption that the part you know is the whole. The Kuiper Belt is not an edge, it is a beginning, the beginning of a frozen wilderness so enormous that the entire planetary system from Mercury to Neptune, every world ever visited by a spacecraft, every photograph ever taken from beyond Earth's atmosphere, every moon and ring and asteroid and comet nucleus that human civilization has ever studied up close, fits inside a fraction of its total extent. If you enjoy journeys that force you to rebuild your understanding of your own place in the cosmos from the ground up, do me a small favor and hit that like button and subscribe. It genuinely helps this channel reach more people who are willing to sit with ideas that are uncomfortable and vast and true. And this one is all 3. Get yourself comfortable. Clear your mind of the diagram you were taught, because what you are about to encounter is not a revision of a detail. It is a revision of the frame itself. Let's begin. Start with the number that the classroom poster always obscures. The distance from the Sun to Neptune is approximately 30 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, roughly 150 million kilometers. So Neptune, the outermost planet, orbits at a distance of about 4.5 billion kilometers from the Sun. That is the outer boundary of the familiar solar system, the edge of the picture, the last labeled circle before the white space begins. Now consider what the white space actually contains. The Kuiper Belt begins at approximately 30 astronomical units, right where Neptune's orbit sits, and extends outward to at least 50 astronomical units from the Sun. Some of its associated populations stretch to 70, 80, even 100 astronomical units or beyond. The main body of the belt alone spans 20 astronomical units of radial distance. That is 2/3 the width of the entire planetary zone, added onto the end of the solar system in a region that most diagrams represent as empty. To feel what those numbers mean, try a different approach. Imagine you could drive a car at highway speed, 100 kilometers per hour, directly away from the Sun toward the inner edge of the Kuiper Belt. You would need to drive continuously, without stopping, for over 5,000 years just to arrive at the belt's beginning. The outer edge would require another 2,000 years of driving beyond that. 7,000 years of unbroken travel at highway speed, through a vacuum in total darkness, with the Sun shrinking steadily behind you, into a point of light no brighter than a bright star. And you would still be inside the main body of the belt, still in the structured, catalogued, relatively well understood portion of the outer solar system. The regions beyond would require centuries more. These are not the distances of interstellar space. These are the distances of your own solar system, the system you live in, the system the diagram on the classroom wall was supposed to represent. The distortion is not accidental. It is a practical necessity. You cannot draw the solar system to scale on any object a human being can hold. If the Sun were the size of a basketball and placed at one end of a football field, Earth would be a peppercorn roughly 26 meters away. Neptune would be a small marble about 800 meters from the basketball, nearly a kilometer down the road. The inner edge of the Kuiper Belt would begin just past that marble and extend outward for another 500 meters. The outer edge of the belt's main body would sit roughly a kilometer and a half from the basketball. The full extent of the scattered disk populations associated with the belt would reach nearly 3 kilometers. On that scale, the entire span from Mercury to Neptune, every named planet, every photographed moon, every spacecraft destination in the history of human exploration fits inside the first 800 meters. Everything beyond that first 800 meters is the Kuiper Belt and the outer wilderness it leads into. And most people have never been shown those additional kilometers at all. This is the first thing the Kuiper Belt demands you understand. The solar system you know is not the solar system. It is the core of the solar system, the innermost region. The warm, bright, relatively crowded lobby of a structure whose true extent stretches outward for distances that no diagram you have ever seen has honestly represented. But the scale alone is not the deepest surprise. The deepest surprise is what actually occupies that space. For most of the history of astronomy, the region beyond Neptune was assumed to be essentially empty. This assumption was not unreasonable. Theoretical models of solar system formation suggested that the density of material in the outer solar nebula would have been too low and the orbital periods too long for significant structures to assemble at those distances. The giant planets Jupiter, Saturn, Uranus, and Neptune had swept up most of the available material in the outer solar system during their formation. Whatever remained would have been scattered, dispersed, reduced to a thin and featureless haze of isolated objects, too sparse and too faint to be worth cataloguing. Pluto, discovered in 1930 by a 24-year-old amateur astronomer named Clyde Tombaugh, working at the Lowell Observatory in Arizona, seemed to confirm this picture. Here was the sole known resident of the outer solar system beyond Neptune, small, cold, solitary, a runt at the back of the line. Textbooks classified it as the 9th planet and described it as sitting at the edge of the solar system, the way a lighthouse sits at the edge of a cliff. Not the beginning of something, the end of something. That framing persisted for 60 years. In 1951, a Dutch-American astronomer named Gerard Kuiper published a paper suggesting that a disk of icy bodies might have once existed in the outer solar system, though he argued it had likely been dispersed over time by Pluto's gravitational influence, which he believed was far greater than it actually is. Around the same period, Irish astronomer Kenneth Edgeworth had independently speculated about a reservoir of small icy bodies beyond Neptune that might supply the solar system with its short-period comets. Neither man could prove his idea. Neither man had the instruments to look. The region was too far, the objects too faint, the technology insufficient. For 4 decades, the outer solar system remained theoretical territory. Maps marked it with the cartographic equivalent of "there be dragons." Scientists acknowledged the possibility of structure out there, but the possibility sat in journals and conference proceedings, not in data, not in confirmed observations, not in the kind of irrefutable evidence that transforms a hypothesis into a fact. 2 astronomers decided to find out which it was. David Jewett was 30 years old when he began his search for Kuiper Belt objects in 1987. Jane Liu was a graduate student in her mid-20s. They worked at the University of Hawaii, using telescopes on the summit of Mauna Kea, one of the best astronomical observing sites on Earth. The task they set themselves was, by any reasonable measure, almost absurdly difficult. They were looking for objects so faint that they registered as barely perceptible smudges at the very edge of what their instruments could detect. Objects millions of times dimmer than the faintest star visible to the naked eye. Objects that moved so slowly against the background of distant stars that the motion was only detectable by comparing images taken hours or nights apart. The technique was straightforward in principle and brutally tedious in practice. Take a long exposure photograph of a small patch of sky near the plane of the solar system. Wait several hours. Take another photograph of the same patch. Place the 2 images side by side, or blink them rapidly back and forth on a screen. A stationary dot in both images is a distant star. A dot that has shifted position, however slightly, is something orbiting the Sun in the outer solar system. Night after night, month after month, year after year, nothing moved. 5 years of searching produced 5 years of absence. The outer solar system returned nothing. The models suggesting emptiness appeared to be right. Jewett later admitted that by 1991 he was beginning to question the entire project. The null result was starting to feel less like the patience required before a discovery and more like the confirmation of a mistake. Then, on the night of the 30th of August 1992, something moved. A faint dot in their images, hovering at the very edge of detectability, had shifted position between exposures at exactly the rate expected for an object orbiting the Sun at roughly 44 astronomical units. It was not a star. It was not a known asteroid. It was not a comet. It was something new. Something that had been waiting in the outer solar system for the entire history of human astronomy, circling the Sun in undisturbed silence while civilizations rose and fell and telescopes grew from Galileo's tube of glass to the precision instruments on Mauna Kea. They designated it 1992 QB1. It had no name. It had no mythology attached to it. It was a catalogue number assigned to a faint smudge of light 4.5 billion kilometers from the Sun. But it was proof. The outer solar system was not empty. Something was out there. And if one object existed, the mathematics of formation strongly implied that many more would follow. A single confirmed detection was not a coincidence. It was a crack in a wall that had been standing for 60 years. Within months, a second object appeared, then a third. Other teams joined the search with their own telescopes and survey programs. Within a decade, improved cameras, larger apertures, and dedicated survey strategies had revealed hundreds of new objects drifting through the darkness beyond Neptune, each one a faint point shifting slowly against the background stars. Each one a confirmation that the white space at the edge of the classroom diagram was not empty. It was full. Not full in the way the inner solar system is full, not crowded with planets and moons and asteroids close enough to influence each other visibly, close enough to catch the light and shine in a night sky. Full in a different way. Full the way a vast ocean is full of fish you cannot see from the surface. Full in a way that requires instruments, patience, and the willingness to look past everything familiar before it reveals itself. The Kuiper Belt had been there the entire time. 4.5 billion years of orbiting the Sun in the cold and the dark, unseen and unmeasured, while every astronomer who ever lived mapped the inner solar system with increasing precision and simply stopped looking before they reached it. It was not a new discovery, it was a correction to the picture, a correction to the diagram, a correction to the story of where you live. And what the correction revealed, once astronomers began to look with real determination, was stranger, more complex, more scientifically significant, and more philosophically unsettling than anyone standing in a Hawaiian observatory in 1987 could have anticipated. The white space at the edge of the poster was not empty space. It was the beginning of a frozen world that dwarfs everything inside it. And you are only now beginning to see it. As of today, astronomers have catalogued over 3,000 individual Kuiper Belt objects. The estimated total population of objects larger than 1 kilometer across is measured in the hundreds of millions. Models suggest there may be more than 100,000 objects in the belt, with diameters exceeding 100 kilometers. 100,000 worlds, each larger than a small city, orbiting in the darkness beyond Neptune, most of them never seen, never named, never visited, never even suspected by the civilization that shares a solar system with them. That number deserves a moment of stillness. 100,000 objects larger than 100 kilometers across, in a single structural zone of the solar system that most people could not describe in any detail if asked. For comparison, the asteroid belt between Mars and Jupiter, the one that appears in every science fiction film as a treacherous gauntlet of tumbling rocks, contains perhaps 1 million to 2 million objects larger than 1 kilometer, but only a handful exceeding 100 kilometers in diameter. The largest, Ceres, measures roughly 940 kilometers across and was reclassified as a dwarf planet in 2006. The total mass of the entire asteroid belt is staggeringly small, roughly 4% of the mass of Earth's moon. Despite its dramatic reputation, the asteroid belt is sparse, lightweight, and physically modest. The Kuiper Belt contains more large objects. It occupies a volume of space so much larger than the asteroid belt that the asteroid belt could fit inside it thousands of times over. And its physical character is entirely different in ways that matter deeply, not just to planetary scientists, but to anyone trying to understand the true nature of the solar system's outer architecture. The difference begins with temperature and composition. The asteroid belt sits between 2 and 3.5 astronomical units from the Sun. At those distances, the Sun's energy is still significant. Surface temperatures on asteroids range from roughly -70 to positive 100 degrees Celsius, depending on distance, composition, and time of day. These are cold conditions by human standards, but warm enough that volatile materials, ices of water, methane, nitrogen, and carbon monoxide cannot survive on exposed surfaces for long geological timescales. They sublimate, driven off by solar radiation, leaving behind the rocky and metallic compositions that characterize most asteroids. Silicate minerals, iron, nickel, basaltic rock. The stuff of the inner solar system, the stuff that built Mercury, Venus, Earth, and Mars. The Kuiper Belt exists in a completely different thermal regime. At 40 astronomical units from the Sun, surface temperatures hover around -220 to -240 degrees Celsius. At 50 astronomical units, they drop even further. These are temperatures at which every substance familiar from daily human experience is locked into a solid state so rigid and so energetically inert that the word frozen fails to capture what it actually means. Water ice at these temperatures does not behave like the ice in your freezer. It behaves like granite. It is mechanically indistinguishable from rock. You could build a mountain range from it, and the mountain range would stand for billions of years without deforming under its own weight. Methane, the gas that heats your stove and warms your home in winter, freezes at -182 degrees Celsius. In the Kuiper Belt, it is a pale crystalline solid, as hard and immobile as any mineral on Earth. Nitrogen, the gas that makes up 78% of every breath you take, freezes at -210 degrees Celsius. In the Kuiper Belt, it exists as a translucent glassy ice, forming plains and glaciers on the surfaces of the largest objects. Carbon monoxide, carbon dioxide, ammonia, ethane, all of them gases or liquids at any temperature a human being has ever experienced directly, all of them frozen solid in the outer solar system, preserved in states that have not changed in any meaningful way since they condensed from the solar nebula 4.5 billion years ago. This is the defining physical characteristic of the Kuiper Belt. It is not a region of rock and metal like the asteroid belt. It is a region of ice, primordial ice. Ice that formed when the solar system was new and has been held at temperatures near absolute zero ever since, undisturbed by the thermal processing that has altered every object in the inner solar system beyond recognition. To understand why this matters, you need to go back to the beginning. Not the beginning of recorded human history, the beginning of everything in this solar system. Approximately 4.5 billion years ago, the Sun formed from the gravitational collapse of a slowly rotating cloud of gas and dust. As material fell inward and the young Sun ignited at the center, the remaining gas and dust flattened into a broad rotating disk surrounding it. This disk, called the solar nebula, was the raw material from which every planet, every moon, every asteroid, every comet, and every Kuiper Belt object eventually formed. The disk was not uniform. Temperature decreased with distance from the young Sun. In the innermost regions, only the most refractory materials, iron, silicates, aluminum oxides, could condense into solid grains. These grains stuck together into larger and larger clumps through a process of gradual accretion, eventually building the terrestrial planets. Mercury, Venus, Earth, and Mars are the end products of that process, assembled from the rocky and metallic materials that could survive the heat of the inner disk. Farther out, beyond a boundary called the frost line, located at roughly 2 to 3 astronomical units from the young Sun, temperatures dropped low enough for water ice to condense alongside rock. This dramatically increased the amount of solid material available for planet building. The giant planets, Jupiter, Saturn, Uranus, and Neptune, formed in this colder zone, accumulating massive cores of rock and ice, and then sweeping up enormous envelopes of hydrogen and helium gas from the surrounding nebula. But not everything in the outer disk became part of a giant planet. Beyond Neptune, the density of material in the solar nebula was lower, and orbital periods were longer. Objects at these distances took so much time to complete a single orbit that the gradual process of accretion never had sufficient opportunity to assemble anything large. The building blocks of a potential outer planet remained as individual chunks, slowly orbiting the young Sun, never gathering the critical mass needed to trigger runaway accretion and become a giant. These frozen fragments are the Kuiper Belt objects. They are planetary construction material that never got used, leftovers from the assembly process. Original pieces of the solar nebula, preserved in a deep freeze so complete that studying them is, in the words of planetary scientist Alan Stern, like finding the original ingredients of a recipe that was cooked 4.5 billion years ago. This is why the Kuiper Belt occupies a position of extraordinary scientific importance that its low public profile does not begin to reflect. The planets have been processed. They have been melted, differentiated, cratered, tectonically resurfaced, atmospherically altered, and in some cases fundamentally transformed from whatever they originally were. Earth's original surface is gone. Mars's original surface is buried under billions of years of geological activity. Even the asteroid belt, relatively cold and geologically quiet by inner solar system standards, has been gravitationally stirred, thermally processed by proximity to the Sun, and altered by 4 billion years of collisions. The Kuiper Belt objects have experienced almost none of this. Their surfaces preserve the chemistry of the solar nebula, with a fidelity available nowhere else in the solar system. Their compositions record the temperature and pressure conditions at specific distances from the young Sun at the moment of condensation. Their structures retain the physical signatures of their formation processes, undisturbed by the geological or thermal activity that has erased those signatures everywhere closer to the Sun. They are fossils, not biological fossils, physical fossils, remnants of a formation process that ended 4.5 billion years ago, preserved by the very conditions that make the Kuiper Belt so hostile and so difficult to study. But here the story takes a turn that complicates the picture in ways that make it simultaneously more confusing and more revealing. The Kuiper Belt did not simply form and remain static. It was shaped. It was sculpted, reorganized, and architecturally restructured by a sequence of events in the solar system's early history that left scars still readable today in the orbital patterns of objects drifting through the outer darkness. And the sculptor was not the sun. It was a planet, Neptune. To understand what Neptune did to the outer solar system, you first need to understand something that most people were never told in their basic introduction to planetary science. The planets did not form in their current orbits and stay there. They moved. In the solar system's first few 100 million years, the giant planets underwent a period of significant orbital migration, shifting their distances from the Sun through a mechanism driven by gravitational interactions with the dense disk of small bodies that surrounded them. Jupiter migrated slightly inward. Saturn, Uranus, and Neptune migrated outward. Neptune's outward migration was by far the most consequential for the outer solar system. Starting from a formation position perhaps 15 to 20 astronomical units from the Sun, Neptune moved outward over tens of millions of years, eventually settling into its current orbit at 30 astronomical units. As it migrated, it swept through the primordial outer disk of icy planetesimals like a hand sweeping through a table covered in scattered objects. The model that describes this migration, developed by a group of planetary scientists at the Observatoire de la Côte d'Azur in Nice, France, and accordingly known as the Nice model, represents one of the most important advances in solar system science of the past 3 decades. It explains features of the outer solar system that no earlier model could account for, and it transforms Neptune from a passive endpoint of the planetary sequence into the active architect of everything that lies beyond it. As Neptune moved outward, its gravitational influence interacted with every icy body in the outer disk. The interactions were not gentle. Some objects were flung inward, sent on trajectories that carried them deep into the inner solar system, where they rained down on the young terrestrial planets in a period of heavy bombardment. The craters that scar the face of the Moon, the ancient impact basins on Mercury and Mars, many of these features may trace directly back to icy bodies dislodged from the outer disk by Neptune's migration and sent falling inward toward the Sun. Other objects were flung outward, given enough velocity to escape the main disk entirely and settle into highly elongated orbits, reaching hundreds or thousands of astronomical units from the Sun. These became the scattered disk population, and their most distant members eventually populated the theoretical Oort cloud, the vast spherical shell of icy bodies at the outer boundary of the solar system's gravitational reach. Still, others were captured into specific orbital patterns called mean motion resonances. A resonance occurs when 2 orbiting bodies complete their orbits in a simple integer ratio of time. An object in a 2 to 3 resonance with Neptune, for example, completes exactly 2 orbits around the Sun for every 3 orbits Neptune completes. This gravitational lockstep creates a repeating pattern of interactions between the 2 bodies that, under the right conditions, stabilizes rather than disrupts the smaller object's orbit. Neptune's outward migration swept through the outer disk like a magnet moving through iron filings, gathering objects into resonances and carrying them along as it advanced. The result of this migration is the Kuiper Belt's current orbital architecture. It is not random, it is not featureless. It is a structured record of Neptune's journey outward, written in the orbital patterns of hundreds of thousands of icy bodies. The most densely populated resonance is the 2 to 3, the one that carries objects along at precisely 2 orbits per 3 Neptune orbits. Objects locked into this resonance are called Plutinos because the most famous of them is Pluto. Pluto is not simply a distant world that happens to orbit beyond Neptune. It is a resonant object, gravitationally coupled to Neptune in a relationship that has stabilized its orbit for billions of years. Despite the fact that Pluto's path actually crosses inside Neptune's orbit at closest approach, the resonance protects it. Neptune and Pluto have never had a close gravitational encounter because their orbital coupling ensures they are always safely separated when they approach the same region of space. Hundreds of other icy bodies share this same gravitational relationship with Neptune. Pluto is not a loner at the edge of the solar system. It is one member of a dynamically defined population, distinguished from its neighbors primarily by its size and its historical accident of being discovered first. Beyond the Plutinos, the classical Kuiper Belt stretches from roughly 42 to 47 astronomical units. This region contains two distinct populations that tell different stories about the solar system's history. The cold classical belt, so named not because of temperature, which is uniformly extreme throughout the outer solar system, but because of the low orbital inclinations of its members, consists of objects on nearly circular, gently tilted orbits. These objects appear to have formed in place and survived Neptune's migration without significant disturbance. Their low-energy orbits suggest they were never strongly scattered or gravitationally perturbed. They are the Kuiper Belt's least disturbed residents, the objects most closely preserving their original formation conditions. The hot classical population occupies similar distances, but with higher orbital inclinations and more elongated paths. These objects were stirred and scattered during the period of planetary migration, their orbits excited into their current configurations by gravitational interactions before settling. Their different dynamical history is written in their orbital parameters and, remarkably, in their colors. Cold classical objects tend to display distinctly reddish surfaces, consistent with long-term surface chemistry undisturbed by thermal or collisional processing. Hot classical objects and scattered disk members tend toward more neutral gray tones, as though their surfaces were processed or modified during the violent era of their excitation. Color in the Kuiper Belt is not decorative. It is data. It encodes the history of where an object came from, what it experienced, and how long it has been where it is. Beyond the classical belt and the resonant populations, the scattered disk stretches outward to distances of 100 astronomical units and beyond. Its members occupy wildly eccentric orbits, swinging from relatively close approaches to Neptune out to distances far beyond the main belt. These are the objects most directly scattered by Neptune's gravitational influence, the ones that received the strongest perturbations during the migration era and settled into the most extreme orbital configurations. They are the Kuiper Belt's most dynamically active population, and they serve as the primary source of the Jupiter family comets that occasionally brighten the inner solar system's night sky. The full architecture of the outer solar system revealed by decades of survey work is therefore not a simple ring of debris. It is a layered, structured system of populations, each occupying a distinct dynamical niche defined by its relationship to Neptune, each recording a different chapter in the story of the solar system's violent early rearrangement. Reading the Kuiper Belt's orbital structure is like reading the rings of a tree, each layer encoding the conditions of a specific era, each gap and concentration pointing back to a gravitational event that reshaped the outer solar system long before any eye existed to witness it. Neptune did not merely sit next to the Kuiper Belt. It created the Kuiper Belt in its current form. Without Neptune's migration, the outer disk would look completely different. The resonant populations would not exist in their current configurations. The sharp inner edge of the belt, which coincides almost precisely with Neptune's orbital position, would not be so cleanly defined. The color and inclination divisions between populations would not map onto each other with the precision that surveys reveal. Every structural feature of the Kuiper Belt is a gravitational fingerprint left by a planet's outward journey 4 billion years ago. And here is what makes this realization sit with particular weight. Before Neptune's migration, the outer disk was far more massive than the Kuiper Belt is today. Estimates suggest the primordial outer disk may have contained 10 to 30 times the mass currently found in the belt. Neptune's passage through that disk scattered most of the original material away, either inward toward the Sun or outward toward interstellar space. The Kuiper Belt as it exists today is not the original outer disk, it is the survivors. The fraction that endured Neptune's gravitational sweep and found stable orbits where they have remained ever since. The objects you are looking at when you study the Kuiper Belt are the ones that stayed. They are 4.5 billion-year-old relics of a solar system that was once more massive, more populated, more dynamically active, and more structurally complex than anything visible today. Neptune's migration erased most of that original structure and replaced it with the sparse, cold, resonance-defined architecture that surveys are now painstakingly mapping. The Kuiper Belt is simultaneously an archive and a wreckage, a collection of original materials preserved in conditions rotates you, arranged into patterns that record the most violent reorganization event in the solar system's history. To study it is to read the story of a catastrophe that happened before the Earth was old enough to have oceans, written in the orbital paths of objects. No telescope on Earth has yet resolved into anything more than a slowly drifting point of light. And this is still only the structure, the bones, the architecture. What lives inside that structure, the actual worlds that populate the cold darkness of the outer solar system, is where the story becomes something far more unexpected. For 76 years, Pluto was alone. From the moment Clyde Tombaugh spotted it, shifting position against the background stars on photographic plates taken in January of 1930, to the confirmation of the first additional Kuiper Belt object in 1992, Pluto occupied a unique and somewhat melancholy position in the human understanding of the solar system. It was the last planet, the final outpost. The runt at the back of the line, smaller than Earth's moon, dimmer than anything else in the planetary sequence, orbiting in a region of the solar system that felt less like a neighborhood and more like an exile. Textbooks gave it a paragraph. Diagrams gave it a dot. School children memorized its name as the period at the end of a sentence that began with Mercury. And the implicit message, never quite stated but always present in the way the story was told, was that Pluto's isolation confirmed what the white space on the diagram suggested. Beyond it, nothing. The solar system had delivered its final entry, and the entry was small and cold and alone. That story was never true. Pluto was never alone. It was simply the first of its kind to be found, the brightest and most easily detected member of a vast population of icy worlds orbiting in the same broad region of the outer solar system. Its apparent isolation was not a fact about the outer solar system. It was a fact about the limits of the telescopes available to study it. The companions were always there, drifting through the same cold darkness, waiting for instruments sensitive enough to reveal them. When those instruments arrived, the picture that emerged was nothing like the one Pluto's lonely status had implied. Begin with Eris. In January of 2005, a team led by astronomer Mike Brown at the California Institute of Technology detected a faint moving object in images taken with the Samuel Oschin telescope at Palomar Observatory. The object was designated 2003 UB313 and would later be formally named Eris, after the Greek goddess of discord. The name would prove appropriate. Initial measurements suggested Eris might be slightly larger than Pluto. Later observations refined its diameter to approximately 2,326 kilometers, making it nearly the same size as Pluto, though slightly more massive. Its orbit is dramatically different from Pluto's. Where Pluto follows a relatively modest elliptical path, ranging from about 29 to 49 astronomical units, Eris traces a highly eccentric trajectory that carries it from roughly 38 astronomical units at its closest approach to the Sun, all the way out to nearly 97 astronomical units at its farthest. A single orbit takes Eris approximately 559 years to complete. At its most distant point, Eris is 3 times farther from the Sun than Pluto. The sunlight reaching it at that distance is so faint that the Sun would appear to an observer standing on its surface as nothing more than an extraordinarily bright star, indistinguishable from its neighbors, except by its luminosity. The surface temperature drops to approximately -240 degrees Celsius. Even by Kuiper Belt standards, this is extreme cold, near the limit of what is physically possible in the solar system's current configuration. Eris has one known moon, named Dysnomia, after the daughter of the goddess of discord. Dysnomia is roughly 600 kilometers in diameter and orbits Eris at a distance of about 37,000 kilometers, completing one orbit every 16 days. The mass of Eris, determined precisely from Dysnomia's orbital parameters, turned out to be about 27% greater than Pluto's mass. Eris is smaller in diameter, but denser, composed of a higher proportion of rock relative to ice than Pluto. The discovery of Eris forced a crisis that had been building quietly in planetary science for years. If Pluto was a planet, Eris had to be one too. It was comparable in size, comparable in mass, similarly composed of rock and ice, similarly orbiting in the outer solar system. There was no scientifically defensible criterion by which Pluto could be classified as a planet, and Eris excluded. But accepting Eris as a planet meant the solar system had 10 planets. And Mike Brown's team was finding more candidates every year. If the criterion for planehood was simply being a round, icy object orbiting the Sun beyond Neptune, the solar system might eventually contain dozens of planets, possibly hundreds. The International Astronomical Union convened in Prague in August of 2006 to resolve the crisis. The result was a new definition of planet that required an object not only to orbit the Sun and achieve hydrostatic equilibrium, the condition of being massive enough for gravity to pull it into a roughly spherical shape, but also to have cleared the neighborhood around its orbit of other debris. Pluto had not cleared its neighborhood, neither had Eris. Neither had any of the other large outer solar system objects being discovered in growing numbers. They were classified as dwarf planets, a new category that acknowledged their physical significance without granting them the full status of the 8 dominant bodies that had gravitationally shaped their orbital zones. The reclassification was controversial. Some planetary scientists objected that the clearing criterion was poorly defined and inconsistently applied. Others argued that the entire exercise was semantically irrelevant, that what mattered was not the label, but the physical reality of these objects, and what they could teach science about the solar system's history. The debate about Pluto's status continues in some form to this day, though the scientific community has largely accepted the dwarf planet framework as a working classification. What matters more than the label is what the discovery of Eris revealed. The outer solar system contained not one but multiple large worlds, and Eris was only the most dramatic example. Makemake was discovered in March of 2005, just 2 months after Eris, by the same team at Palomar. It orbits in the classical Kuiper Belt at an average distance of approximately 45 astronomical units, following a moderately eccentric path that keeps it between 38 and 53 astronomical units from the Sun. Its diameter is roughly 1,430 kilometers, placing it comfortably in the dwarf planet category. The surface is dominated by frozen methane and ethane, giving it a distinctly reddish appearance, consistent with the Tholin chemistry expected for a cold classical object that has spent billions of years under low-intensity ultraviolet irradiation. Makemake has one known moon, designated S, 2015 Mk2, roughly 175 kilometers in diameter, discovered in 2016 using the Hubble Space Telescope. The moon's orbit is highly inclined relative to Makemake's equatorial plane, suggesting it may have been captured rather than formed in place, or that it is the product of an ancient oblique impact that left the larger body's rotation axis and the smaller fragment's orbit misaligned. Then there is Haumea. Haumea is the strangest large object in the Kuiper Belt. Its average orbital distance of approximately 43 astronomical units places it squarely in the classical belt, and its diameter along its longest axis reaches roughly 2,300 kilometers, comparable to Eris and Pluto. But Haumea is not a sphere. It cannot be a sphere. It rotates so rapidly, completing one full rotation in less than 4 hours. That centrifugal force has stretched it into an elongated ellipsoid, shaped roughly like a flattened rugby ball, with dimensions of approximately 2,000 kilometers along the longest axis, and approximately 1,000 kilometers along the shortest. Its polar regions are pulled inward, while its equator bulges outward, a shape driven entirely by the physics of rapid rotation acting on a self-gravitating body. The rotation rate is almost certainly the result of a massive collision in the distant past. Some large impactor struck Haumea hard enough, and at the right angle, to set it spinning at this extraordinary speed. The collision also produced a family of smaller icy fragments, sharing similar orbital parameters, the only confirmed collisional family in the entire Kuiper Belt. Haumea's 2 known moons, Hi'iaka and Namaka, may themselves be remnants of this ancient impact, pieces of Haumea's surface blasted into orbit and never recaptured. In 2017, astronomers detected a ring around Haumea, the first ring ever identified around a trans-Neptunian object. The ring orbits at a distance of roughly 2,287 kilometers from Haumea's center, composed of material thin enough that it was only detectable through a stellar occultation campaign in which multiple telescopes across Europe observed the precise dimming pattern as Haumea passed in front of a distant star. The ring's existence suggests that ring systems are not limited to the giant planets of the inner solar system. They may be a common feature of sufficiently large or rapidly rotating outer solar system objects. And then there is Kuiper. Kuiper orbits at approximately 43 astronomical units in the classical belt, with a diameter of roughly 1,110 kilometers. For years, it was a reasonably well-characterized, if unremarkable, member of the dwarf planet candidate population. Then in 2022, astronomers detected something around it that should not have been there. A ring, but not just any ring. The ring orbits Kuiper at a distance of roughly 4,100 kilometers from the object's center. That distance is the problem. For context, every ring system ever previously observed around a solar system body, Saturn, Uranus, Jupiter, Neptune, and Haumea, orbits inside what is called the Roche limit. The Roche limit is the distance from a body inside which tidal forces are strong enough to prevent small particles from clumping together under their own gravity. Inside the Roche limit, material remains dispersed as a ring. Outside it, material should gradually coalesce into a moon. Kuiper's ring orbits well outside its Roche limit. At 4,100 kilometers, the ring material should have aggregated into a moon long ago. The fact that it persists as a ring violates the conventional theoretical framework for ring formation and maintenance that planetary scientists had considered essentially settled for decades. The leading hypothesis involves the extreme cold of the Kuiper Belt. At temperatures near -230 degrees Celsius, the surface material of ring particles may be so brittle and so poorly elastic that collisions between them do not result in the gentle sticking behavior that leads to accretion. Instead, particles shatter. Each collision produces smaller fragments rather than larger ones, perpetually recycling the ring material into a population too fragmented to self-aggregate. The cold itself may be the mechanism that preserves the ring against the gravitational pressure to collapse. If this explanation is correct, it implies that rings around cold outer solar system objects may behave by different physical rules than rings around the warmer giant planets, and that the theoretical framework developed for Saturn's rings may need modification before it can be applied universally. A ring around a Kuiper Belt object is not merely an exotic curiosity. It is a laboratory for testing the limits of our understanding of basic physical processes. In early 2025, additional observations of the Kuiper system suggested evidence for a possible second moon, in addition to its previously known companion Weywot, making it potentially one of the most complex small worlds in the outer solar system. The confirmation awaits further observation, but the pattern it suggests is consistent with a broader trend that has become impossible to ignore as Kuiper Belt surveys have accumulated data. The outer solar system is not populated by simple, geologically inert ice balls. It is populated by complex, structured, dynamically rich worlds with rings, multiple moons, and physical behaviors that continue to challenge theoretical models. These 5 objects, Pluto, Eris, Makemake, Haumea, and Kuiper, are simply the most prominent members of a far larger community. Dozens of additional Kuiper Belt objects exceed 500 kilometers in diameter. Hundreds exceed 200 kilometers. Each is large enough to have achieved hydrostatic equilibrium, meaning each has been pulled by its own gravity into a roughly spherical shape. Each is, by the physical definition of the term, a world, a discrete body with a surface, a composition, an internal structure, and a history extending back to the formation of the solar system. The Kuiper Belt contains more dwarf planets than any other region of the solar system, more than the asteroid belt, more than the region of the giant planets. The outer solar system, the region most people regard as empty space beyond the last real planet, is in fact the most densely populated zone of worlds in the entire solar system, measured by the number of gravitationally rounded objects per unit of radial distance from the Sun. And almost none of them have been studied up close. Almost none of them have been visited. Almost none of them have been imaged at resolutions sufficient to reveal anything about their surfaces, their geology, or their internal structures. They are known as points of light and orbital parameters, as diameter estimates derived from thermal emission measurements and density calculations inferred from the orbits of their moons. The physical reality of what they actually look like, what processes shape them, what their surfaces feel and sound and smell like, is almost entirely unknown. Almost. Because there is one exception. One Kuiper Belt object has been visited, one has been imaged in detail, one has had its surface mapped, its atmosphere measured, its mountains named, its geological features catalogued and debated and written about in hundreds of scientific papers, since a spacecraft the size of a baby grand piano flew past it at 14 kilometers per second in the summer of 2015. But before that visit, before the first close look at a Kuiper Belt world, there is another story to tell, a story about shapes, about the way things form, about a small two-lobed object drifting through the cold classical belt at 44 astronomical units from the Sun, preserving in its physical structure a record of the solar system's earliest moments that no other object in the known solar system can match. Arrokoth. The object was discovered in 2014 using the Hubble Space Telescope as part of a dedicated search for potential flyby targets for the New Horizons spacecraft after its Pluto encounter. It was then known by a series of temporary designations, most commonly the informal nickname Ultima Thule, a phrase meaning beyond the known world. The formal name Arrokoth, derived from the Powhatan word for sky, was assigned in 2019 after the flyby. It orbits in the cold classical belt at approximately 44 astronomical units from the Sun on a nearly circular, low-inclination path consistent with a body that formed in place and was never significantly disturbed by Neptune's migration. Before New Horizons arrived, Arrokoth was a faint smudge in Hubble images. Its light curve, the pattern of brightness variation as it rotated, suggested an elongated shape, but the resolution was insufficient to determine whether it was a single elongated body or two distinct objects. Scientists suspected it might be a contact binary, two separate lobes touching at a narrow neck, but could not confirm it from Earth. When the images arrived from the spacecraft on the 1st of January 2019, the confirmation was immediate and striking. Arrokoth is a contact binary, two flattened lobes connected at a narrow neck, forming a shape that has been compared to a snowman, a peanut, and a dented hamburger patty placed gently against a walnut. The larger lobe, designated Ultima, measures roughly 22 kilometers in its longest dimension. The smaller lobe, designated Thule, measures roughly 14 kilometers. Together, they form an object roughly 36 kilometers long, the most distant and most primitive solar system body ever visited by a spacecraft. What the images revealed about how Arrokoth formed was more significant than the shape itself. The two lobes show no signs of violent collision. Their surfaces are smooth, gently curved, and compositionally uniform. The neck connecting them is narrow but structurally intact, not crushed or shattered the way it would be if two objects had impacted at significant relative velocity. The colors of both lobes are identical, a uniform reddish tone, consistent with long-term Tholin chemistry on a surface that has never been significantly altered by heat or collision. Everything about the physical appearance of Arrokoth points toward a gentle assembly, a slow coming together of two objects that were gravitationally bound long before they actually touched. The most widely accepted explanation is gravitational collapse within the solar nebula, a localized concentration of small icy particles in the outer disk, enhanced by a process called the streaming instability, in which solid particles interact aerodynamically with surrounding gas and concentrate into dense filaments, reached sufficient density to collapse under its own gravity. The collapsing cloud separated into two clumps that began orbiting each other at low relative velocities, while simultaneously spiraling inward. Over thousands of years, the two lobes drew closer and closer until they made contact. Not a collision, a gentle touchdown. The relative velocity at the moment of contact was probably no more than a few meters per second, slow enough that a person walking briskly could have outpaced it. The resulting object locked the original shapes of both clumps almost perfectly into a permanent frozen record, like two scoops of ice cream placed carefully side by side and then sealed in a freezer cold enough to preserve them forever. This mechanism, the streaming instability leading to gravitational collapse and binary formation, had been predicted theoretically for years before Arrokoth was visited. The predictions suggested that it should be the dominant formation pathway for small bodies in the outer solar system. Arrokoth was the first direct observational confirmation that the predictions were correct. Its shape is not an accident. It is a signature, a physical record of the process by which the Kuiper Belt's population assembled itself from raw material in the solar nebula over 4.5 billion years ago. The implications extend far beyond the Kuiper Belt. If streaming instability and gravitational collapse are the dominant mechanisms for forming small outer solar system bodies, then the same processes likely operated throughout the protoplanetary disk during the solar system's formation. The building blocks that eventually assembled into the terrestrial planets and the cores of the giant planets may themselves have formed through similar collapse events. Arrokoth does not merely tell the story of one small object in the cold classical belt. It tells the story of how the solar system's fundamental building blocks came into existence. Since the Arrokoth flyby, further work has strengthened this conclusion. In February of 2026, a study published in the monthly notices of the Royal Astronomical Society provided detailed computer simulations by Jackson Barnes, a graduate student at Michigan State University, demonstrating that a spinning cloud of pebble-sized material can collapse, separate into two gravitationally bound lobes, and bring those lobes into gentle contact without shattering either one. The simulations reproduced a wide range of two-lobed shapes with varying lobe sizes and proportions, matching the diversity of contact binary shapes observed throughout the Kuiper Belt. The agreement between simulation and observation was not marginal. It was precise enough to leave little room for alternative explanations. Arrokoth is not an outlier in the Kuiper Belt population. Light curve studies of other small Kuiper Belt objects reveal that a significant fraction, estimates range from 10 to 30%, display brightness variations consistent with elongated or bilobed shapes. The cold classical belt may be populated by millions of snowman-shaped relics of gravitational collapse, each one a frozen record of the solar system's earliest formation processes, each one drifting through the outer darkness in a state of preservation so complete that studying them is genuinely equivalent to reading the original manuscript of the solar system's history, rather than a translation made billions of years after the fact. These objects are not exotic anomalies found at the edge of scientific understanding. They are the most direct physical evidence available for how planetary systems form. They are more informative, in some respects, than any planet in the solar system, because the planets have been so thoroughly processed and altered by geological and atmospheric activity that their original formation signatures are gone. The Kuiper Belt preserves those signatures in deep freeze, intact, unmodified, waiting. The cold that makes the Kuiper Belt so hostile to human existence is the same cold that makes it scientifically irreplaceable. The darkness that makes it invisible to casual observation is the same darkness that has protected its contents from the thermal processing that would have erased the very information scientists most want to read. The Kuiper Belt is hostile, and its hostility is the reason it matters. But knowing what these worlds are, what they are made of, how they formed, and what they preserve is still different from actually seeing one up close. From having a spacecraft cross the threshold and return images detailed enough to reveal mountains, glaciers, atmospheric haze, and geological features no theoretical model predicted. That crossing happened, and what it found was more surprising than almost anyone had dared to expect. On the 14th of July, 2015, a spacecraft no heavier than a grand piano completed a journey of 9.5 years and nearly 5 billion kilometers to deliver humanity its first close look at a world in the Kuiper Belt. The approach had been building for weeks. As New Horizons closed the final distance to Pluto, its long-range reconnaissance imager began returning images of increasing resolution, each one revealing a little more detail than the last, each one replacing the fuzzy, pixelated blob that represented the best Earth-based view of Pluto with something that began, slowly and then all at once, to look like a world, a real world, a place with features, with contrast, with structure. The mission team at the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, had been waiting for this moment for over a decade. Principal investigator Alan Stern had spent 15 years fighting to get New Horizons funded, launched, and pointed at Pluto. The spacecraft had been traveling since January of 2006. It had crossed the orbit of the Moon in 9 hours. It had passed Mars in less than 3 months. It had used Jupiter's gravity as a slingshot to accelerate further outward. And then it had traveled for 8 more years through the emptiness of the outer solar system, a small metal object moving through a void so vast that even at 14 kilometers per second, the journey consumed the better part of a human decade. Closest approach came at 11:36 in the morning, Eastern Time. At that moment, New Horizons was 12,500 kilometers from Pluto's surface, traveling so fast that the entire encounter, the window during which the spacecraft was close enough to gather high-resolution data, lasted only a matter of hours. There was no possibility of slowing down, no option to orbit, no chance to linger. Everything the mission would ever learn about Pluto from close range had to be gathered in a single high-speed pass. The spacecraft was pointed away from Earth during the closest approach, its instruments aimed at Pluto rather than the antenna dish pointed homeward. This meant the team received no real-time confirmation that the flyby had succeeded. They had to wait. The signal confirming a successful encounter, traveling at the speed of light across nearly 5 billion kilometers of empty space, took 4 hours and 25 minutes to arrive. When it came, the room erupted. But the celebration was only the beginning. The data itself, stored on the spacecraft's solid-state memory during the flyby, would take over a year to transmit back to Earth across the immense distance. The downlink rate was painfully slow, roughly 1 to 2 kilobits per second, a connection speed slower than a telephone modem from the 1980s. Images and measurements that took milliseconds to record required months to transmit. Scientists received Pluto's secrets in a slow trickle, parcel by parcel, as the months passed, and the data queue gradually emptied across the light hours separating the spacecraft from home. What came back rewrote the textbooks. The expectation going into the flyby was informed by decades of theoretical modeling and indirect observation. Pluto was small, roughly 2,370 kilometers in diameter, smaller than Earth's moon. Its surface gravity was only about 6% of Earth's. Its surface temperature hovered around negative 230 degrees Celsius. Its distance from the Sun meant it received approximately 1/1600th the solar energy delivered to Earth. Every theoretical model, every calculation about the thermal budget available to drive geological activity pointed toward the same conclusion. Pluto should be dead, geologically dead, thermally inert. A frozen relic whose surface had not changed in any meaningful way since the inner solar system's heavy bombardment ended roughly 4 billion years ago. The expectation was craters, endless craters, a surface pockmarked by billions of years of impacts, unmodified by any internal process, unchanged since the solar system was young, a world that had simply been sitting in the cold darkness, accumulating impact scars and nothing else for the entire history of life on Earth. The first high-resolution images ended that expectation permanently. The western hemisphere of Pluto is dominated by a vast, bright feature shaped unmistakably like a heart, stretching roughly 3,000 kilometers across. The mission team named it informally the Heart, and it was later formally designated Tumbor Regio in honor of Clyde Tumbor, the young astronomer who had discovered Pluto 85 years earlier. The left lobe of the Heart, a roughly circular basin approximately 1,000 kilometers in diameter, would become the most scientifically significant single feature observed on any Kuiper Belt object. It is called Sputnik Planitia. Sputnik Planitia is filled with nitrogen ice to a depth of several kilometers, Its surface is divided into irregular polygonal cells, each roughly 30 to 40 kilometers across, separated by shallow troughs. These cells are not random. They are the surface expression of a process operating beneath the visible surface. Warmer nitrogen ice, heated by trace amounts of geothermal energy rising from Pluto's rocky core, becomes slightly less dense than the surrounding material and rises toward the surface. It spreads outward across the basin floor, cools, and sinks back down at the edges of each cell, only to be warmed again and rise once more in a slow, continuous cycle. This process is called convection. You can observe a simplified version of it in a pot of water approaching a boil, where warmer fluid rises from the bottom, spreads across the surface, cools, and sinks again in circular patterns. In Sputnik Planitia, the same physics operates, but on nitrogen ice instead of water, at temperatures near -230 degrees Celsius, on timescales of roughly 500,000 years per overturned cycle. The basin contains no visible impact craters. On a surface in a region of the solar system where cratering should be the dominant process, where billions of years of accumulated impacts should have left a landscape as heavily scarred as the ancient highlands of the moon, Sputnik Planitia presents a surface so young, so continuously renewed by convective overturn, that no crater has had time to survive. The convection erases them. New material rises, spreads, and buries any impact scar before it can become a permanent feature. This is geological activity. On a world whose entire thermal budget, measured in the watts of energy available from radioactive decay in its rocky core, is smaller than the heat output of a modest campfire. On a world where the sun delivers less energy per square kilometer than a birthday candle viewed from across a football field. On a world that every theoretical model had declared should have been geologically silent for 4 billion years. Pluto was active, not in the violent volcanic sense of Earth or Io, quietly, slowly, persistently active. Its interior retained just enough heat to drive a process that continuously renewed the surface of its largest nitrogen ice basin. And that quiet activity was sufficient to produce one of the smoothest, most geologically young surfaces in the entire solar system. Around the edges of Sputnik Planitia, the terrain changed dramatically. Mountain ranges of water ice rose abruptly from the basin margins, reaching heights of 3 to 4 kilometers above the surrounding plains. On Earth, mountains of this scale require tectonic forces, colliding continental plates, volcanic uplift, the kind of energetic geological processes driven by a large and still hot planetary interior. On Pluto, the mountains are made of water ice, not because Pluto has liquid water, but because at Kuiper Belt temperatures, water ice is mechanically equivalent to rock. It is rigid, strong, capable of supporting steep slopes and sharp peaks for billions of years without deforming under its own weight. These are not metaphorical mountains, they are real topographic features, comparable in height to significant mountain ranges on Earth, built from a material that would be liquid on any world closer to the Sun. The water ice that forms Pluto's bedrock is the structural equivalent of granite at these temperatures. Its mountains are as geologically valid as the Rockies or the Alps. They simply exist in a place where the medium of construction is ice rather than silicate rock. Bladed ridges of methane ice, called penitentes after similar features found in high-altitude regions of the Andes on Earth, extend for hundreds of kilometers in some regions of Pluto's surface. Their sharp profiles are shaped by sublimation patterns, the direct conversion of surface ice to gas driven by the angle and intensity of incoming sunlight. Even at Pluto's enormous distance from the Sun, the geometry of illumination is sufficient to sculpt these razor-edged formations over geological timescales. The Sun, reduced to a point of light in Pluto's sky, still does work, still shapes surfaces, still drives processes, slowly and patiently, across billions of years. Tectonic fractures cut across Pluto's surface in long linear systems that run for hundreds of kilometers. These are extensional features, cracks formed when the outer shell of the world was pulled apart under tension. The mechanism that produces this tension is the same one proposed for several icy moons of the outer planets. If Pluto harbors a subsurface ocean of liquid water, The gradual freezing of that ocean over geological time would cause the water to expand as it transitioned to ice. The expanding interior would push outward against the overlying shell, stretching it and tearing it along lines of weakness. The fractures you see on Pluto's surface may be the scars of billions of years of slow internal expansion driven by a hidden ocean freezing from the outside in. The possibility of a subsurface ocean on Pluto was one of the most consequential scientific implications of the entire New Horizons mission. Thermal models developed after the flyby suggest that a layer of liquid water, possibly mixed with ammonia acting as an antifreeze, could persist beneath Pluto's ice shell to the present day. The heat source would be residual radioactive decay in the rocky core, faint, diminishing over geological time, but potentially sufficient to maintain a thin liquid layer at the base of the ice shell, insulated from the negative 230-degree surface by kilometers of frozen nitrogen and water ice above it. If this ocean exists, Pluto is not the dead world the models predicted. It is a world with a liquid interior, separated from the frozen vacuum of the outer solar system by nothing more than a shell of ice. A world where the conditions necessary for liquid water, and therefore at least the physical prerequisites for chemistry of the kind associated with life, persist in secret beneath a surface cold enough to freeze nitrogen solid. Pluto joins a growing list of outer solar system worlds, Europa, Enceladus, Titan, Ganymede, that may harbor liquid water beneath icy exteriors. What was once considered an exclusively inner solar system phenomenon, the maintenance of liquid water by proximity to a warm star, has been progressively revealed as something far more general. Liquid water appears to be common in the outer solar system, sustained not by sunlight but by the slow decay of radioactive elements in rocky cores, by tidal heating from gravitational interactions, by the insulating properties of thick ice shells that trap internal heat against the encroaching cold of the outer solar system. If Pluto can do this, what about the hundreds of other comparably sized Kuiper Belt objects that have never been visited? If even a fraction of them retain enough internal heat to maintain liquid layers beneath their surfaces, the outer solar system may contain far more liquid water environments than the entire inner solar system combined. Water, the medium most closely associated with life as we understand it, may be more abundant in the cold darkness beyond Neptune than anywhere in the warm, sunlit region where human civilization arose. This is not a confirmed finding. It is an implication supported by evidence, but not yet proven. But the implication alone is sufficient to transform how scientists think about the Kuiper Belt's relationship to the broader question of where, in the solar system and beyond, the conditions for complex chemistry can be sustained. Pluto's atmosphere added another layer of surprise. The world possesses a thin but measurable envelope of gas, composed primarily of nitrogen with traces of methane and carbon monoxide. The surface pressure is approximately 100,000 times lower than Earth's atmospheric pressure, a level so rarefied that it would register as a near-perfect vacuum by any industrial or laboratory standard. Yet this wispy atmosphere extends hundreds of kilometers above the surface, far higher than theoretical models had predicted, and it is structured. New Horizons detected distinct haze layers stacked in bands, visible in backlit images, taken as the spacecraft looked back at Pluto from the far side of the encounter, the sun illuminating the atmospheric haze from behind in a crescent of diffuse light that revealed a complexity no model had anticipated. The haze layers are composed of tiny tholin particles, complex organic molecules assembled when ultraviolet light from the distant sun breaks methane molecules apart in the upper atmosphere and triggers a cascade of chemical reactions that build increasingly complex carbon-based compounds. These particles settle slowly toward the surface over time scales of years, contributing to the dark, reddish organic deposits observed in Pluto's equatorial regions. Pluto's atmosphere is not simply a passive envelope of gas. It is an active chemical factory, assembling organic molecules from simple raw materials using nothing but faint ultraviolet light from a star, so distant it appears as a point, producing the same classes of compounds that are thought to have seeded the early Earth with the precursor molecules of biology. Pluto's orbit is eccentric enough that its distance from the Sun varies significantly over its 248-year orbital period. At closest approach, it reaches about 29 astronomical units. At its farthest, it retreats to nearly 50 astronomical units. This variation drives seasonal cycles of atmospheric expansion and contraction. As Pluto moves closer to the Sun, surface temperatures rise fractionally, volatile ices sublimate into gas, and the atmosphere inflates. As it recedes, temperatures fall, gases condense back onto the surface, and the atmosphere thins. At the coldest point in Pluto's orbit, the atmosphere may collapse almost entirely, precipitating as a thin frost on the surface until the next approach brings the warmth needed to revive it. A slow cosmic breath, inhaled and exhaled once every 2.5 centuries. Everything described so far concerns Pluto itself, but New Horizons carried enough instruments and enough observing time to turn its attention to Pluto's largest companion as well, Charon. With a diameter of roughly 1,212 kilometers, Charon is more than half the size of Pluto. No other moon in the solar system is so large relative to its parent body, with the possible exception of certain dwarf planet systems. The two worlds are tidally locked to each other, each presenting the same face to the other at all times as they orbit their common center of gravity once every 6.4 days. That center of gravity, the barycenter of the Pluto-Charon system, lies not inside Pluto but in the empty space between the two bodies, approximately 900 kilometers above Pluto's surface. They orbit each other like two dancers spinning in place, each one always facing the other, separated by approximately 19,600 kilometers of vacuum. No other known planetary system in the solar system exhibits this mutual tidal locking. It makes Pluto and Charon less a planet and moon in the conventional sense, and more a true binary world, two distinct bodies sharing a gravitational partnership so intimate that neither can turn away from the other. New Horizons revealed that Charon's surface tells a completely different story from Pluto's. Where Pluto is coated in volatile nitrogen and methane ices that sublimate and migrate with the seasons, Charon's surface is dominated by water ice. Stable, inert, unchanging at these temperatures. The volatile chemistry that makes Pluto's surface so visually complex and scientifically rich is largely absent from Charon. The moon presents a more muted landscape, older and more heavily cratered than Pluto's resurfaced plains, its history written in impact scars rather than in active geological processes. But Charon is far from featureless. Its north polar region is capped by a dark reddish deposit that the mission team informally named Mordor Macula. The feature is striking in its extent and uniformity, roughly circular, covering the entire polar cap, and composed of material distinctly darker and redder than the surrounding water ice terrain. The explanation connects directly to Pluto's atmosphere, and it is one of the most unusual chemical processes observed anywhere in the solar system. Methane molecules escaping from Pluto's thin atmospheric envelope drift across the 19,600 kilometers of vacuum separating the two worlds. When they reach Charon, some of these molecules become cold-trapped on the polar surface during the decades-long polar winter. When the pole is tilted away from the distant sun and temperatures drop low enough to prevent the methane from immediately sublimating away. Gradually, over thousands of years, a layer of methane frost accumulates on Charon's poles. When the polar region eventually rotates back into sunlight, ultraviolet radiation from the distant sun processes the accumulated methane into tholins, the same complex organic compounds found on Pluto's surface and on the surfaces of countless other Kuiper Belt objects. The result is a growing deposit of dark reddish organic material on Charon's poles, fed continuously by Pluto's escaping atmosphere, processed by solar radiation, and accumulating over millions of years into the feature New Horizons observed. It is atmospheric chemistry conducted across the vacuum of space between two worlds, a process with no known parallel anywhere else in the solar system. A form of chemical exchange operating at a scale and in conditions that had never been observed before a spacecraft crossed 5 billion kilometers to look. Charon's equatorial zone revealed something even more dramatic than its stained poles. A canyon system stretching across the moon's entire midsection, running for over 1,600 kilometers and plunging to depths of up to 9 kilometers in places. For reference, the Grand Canyon of the Colorado Plateau reaches a maximum depth of approximately 1.8 kilometers. Charon's equatorial rift is 5 times deeper, carved across a world 1/10 the diameter of Earth, in a region of the solar system where no geological force was supposed to be operating at any significant level. The canyon system is most likely an extensional feature, formed when Charon's outer shell was subjected to tremendous tensional stress as the interior expanded. The expansion mechanism, by now a familiar pattern in the outer solar system, almost certainly involved the gradual freezing of a subsurface ocean. If Charon once harbored liquid water beneath its ice shell, the transition of that water to ice would have increased its volume, pushing outward against the crust and tearing it apart along the moon's equatorial belt. The canyon system is the scar of that ancient event, a permanent record carved into Charon's face of a process that happened billions of years ago and left the moon geologically silent ever after. The possibility that both Pluto and Charon once possessed, and may still possess, subsurface liquid water is among the most profound findings of the entire New Horizons mission. These are not large worlds. They are not particularly close to the sun. They receive almost no solar energy. They have no tidal heating from a massive nearby giant planet to supplement their meager geothermal budgets. And yet the evidence points consistently toward internal processes driven by the slow decay of radioactive elements in their rocky cores, sufficient to maintain liquid water environments for timescales measured in billions of years. If this can happen on Pluto and Charon, the implications for the broader Kuiper Belt population are staggering in their scope. There are dozens of Kuiper Belt objects comparable in size to Pluto and Charon, each one a world with a rocky core, an icy mantle, a cold surface, and a history extending back to the formation of the solar system. If even a fraction of them share the same internal thermal structure, the same pattern of radioactive decay sustaining a thin liquid layer against the encroaching cold, then the Kuiper Belt is not a region of frozen, geologically dead objects. It is a region scattered with worlds that quietly maintain liquid interiors beneath their frozen surfaces, unseen and unmeasured, orbiting in the darkness beyond Neptune, while the civilization that shares their solar system remains almost entirely unaware of their existence. This is what New Horizons found when it crossed the threshold in 2015, not the dead world the models predicted, not the inert ball of ice that 4 decades of theory had described. A world of convecting nitrogen glaciers, water ice mountains, tectonic fractures, organic atmospheric chemistry, and possibly a hidden ocean. A world that should have been geologically silent and turned out to be quietly, persistently, remarkably alive. And then, 3.5 years later, the spacecraft delivered a second revelation, a smaller one in the sense of physical scale, but in its scientific significance, arguably even more important than everything Pluto had shown. On the 1st of January, 2019, as the rest of the world celebrated the turning of a new year, New Horizons flew past Arrokoth. The images confirmed the contact binary structure that pre-encounter light curves had suggested. 2 flattened lobes, reddish and smooth, connected at a narrow neck. No violent collision history. No significant cratering. No signs of any thermal or geological processing. A surface that had remained essentially unchanged since the moment the 2 lobes first came to rest against each other, more than 4 billion years ago. What Arrokoth lacked was as scientifically significant as what it possessed. It lacked craters in the numbers that collision models had predicted. Its surface was eerily smooth at small scales, suggesting either that the cold classical belt contains far fewer small impactors than models expected, or that some process erases the smallest impact features over time. Either interpretation carries implications for understanding the collision environment of the outer solar system and the size distribution of its smallest members. But what Arrokoth most powerfully lacked was any sign of the violent history that characterizes almost every other body in the solar system examined up close. No catastrophic impacts, no tectonic disruption, no thermal alteration, nothing but the slow accumulation of cosmic ray damage and tholin chemistry on a surface that has been undisturbed for longer than life has existed on Earth. Arrokoth is what the outer solar system looks like when nothing has happened to it, when the 4.5 billion years since formation have passed without incident, when no large impactor has reshaped it, no nearby planet has scattered it, no proximity to the Sun has processed its surface chemistry. It is the baseline, the default state of the cold classical Kuiper Belt, unmodified and uninterrupted. And the baseline is a snowman drifting in the dark, assembled gently from a collapsing cloud of pebbles before the Earth existed, preserved in a cold so absolute that not a single molecule of its surface ice has moved in 4 billion years. New Horizons is still traveling. It crossed Arrokoth's orbit and continued outward into the Kuiper Belt, its instruments still collecting data, its dust counter still measuring particle impacts against the hull, its plasma sensors still sampling the tenuous material of the outer solar system. What those instruments found as the spacecraft moved deeper into unexplored territory was something that nobody had predicted, a signal that did not behave the way the models said it should. A measurement that suggested the Kuiper Belt might not end where everyone assumed it did, and that the outer solar system might be hiding something in the regions beyond the edge of the known map. That discovery, and what it implies about the true extent of the solar system's outer frontier, is where this story turns next. Every model has an edge, a boundary beyond which the predictions stop and the unknown begins. For decades, the models describing the Kuiper Belt placed that edge at approximately 50 astronomical units from the Sun. The reasoning was straightforward and well supported by observation. Survey data showed that the number of detectable Kuiper Belt objects, the known population of classical belt objects, clustered between 30 and 50 astronomical units, with the density of detectable bodies falling off steeply past that outer boundary. Theoretical models explained this drop-off as a consequence of Neptune's migration. When Neptune moved outward through the primordial disk of icy planetesimals, its gravitational influence scattered objects both inward and outward. The objects that settled into the classical belt occupied a relatively narrow zone, defined by the reach of Neptune's resonant and non-resonant gravitational influence. Beyond 50 astronomical units, Neptune's sculpting power diminished, the density of surviving material fell, and the belt effectively ended. This was not a speculative prediction. It was a model grounded in decades of survey work, supported by the orbital statistics of thousands of detected objects, consistent with the broader theoretical framework of planetary migration and disk evolution. The 50 astronomical unit boundary was not drawn arbitrarily. It emerged from the data. New Horizons carried an instrument designed to test it directly. The Venetia Burney Student Dust Counter was built by undergraduate and graduate students at the University of Colorado Boulder, named after the 11-year-old English schoolgirl who had suggested the name Pluto when the planet was discovered in 1930. The instrument measures the rate at which microscopic dust particles strike the spacecraft as it moves through space. Dust in the outer solar system originates primarily from collisions between larger Kuiper Belt objects and from impacts of interstellar dust grains on KBO surfaces. By tracking how frequently dust particles hit the detector, the instrument effectively maps the density of collisional activity in the regions through which the spacecraft passes. More collisions between larger objects produce more dust. Higher dust density means more objects in the vicinity. Lower dust density means fewer. The prediction was clear. As New Horizons moved outward past the main body of the classical belt, through 45, then 50, then beyond 50 astronomical units, the dust count should decline. The population of objects producing the dust was supposed to thin out past that boundary. The spacecraft should have been flying into progressively emptier space, recording fewer impacts per unit time as it left the structured belt behind and entered the vast, nearly featureless void between the classical belt and the theoretical inner edge of the Oort cloud. The instrument did not read what the models predicted. Between roughly 45 and 60 astronomical units, the dust counter recorded impact rates that exceeded model expectations. The signal did not fade as the spacecraft moved past 50 astronomical units. It persisted. It remained elevated through a region where the known population of Kuiper Belt objects had fallen to near zero in ground-based surveys. Something out there was still producing dust. Something was still colliding, still generating the microscopic debris that the student-built instrument was faithfully recording, impact by impact, as New Horizons traveled deeper into territory no spacecraft had ever sampled before. The data were published in a paper in the Astrophysical journal Letters in early 2024. The authors, led by Alex Doner of the University of Colorado Boulder, presented two possible interpretations. The first was that the classical Kuiper Belt simply extends farther outward than current models estimate. The drop-off in detected objects near 50 astronomical units might reflect the limits of ground-based survey sensitivity, rather than a true physical boundary in the belt's population. Objects beyond 50 astronomical units are fainter, slower moving, and harder to detect from Earth. If surveys have been systematically missing a population of objects in the 50 to 80 astronomical unit range because those objects are too faint for existing telescopes to reliably find, the dust signal from New Horizons would be exactly what you would expect. The belt is there, the surveys just have not been sensitive enough to see it. The second interpretation is more dramatic. The elevated dust levels might indicate a second, previously unknown population of icy bodies existing beyond the classical belt. A separate outer ring, or extended debris field, physically distinct from the main Kuiper Belt, generating its own dust through mutual collisions in a region that ground-based surveys have classified as empty, simply because no object there has yet been detected. Not an extension of the known belt, a new structure entirely. Both interpretations carry profound implications, but in different directions. An extended belt means the solar system's outer architecture is larger than the standard model describes. The boundary that textbooks and diagrams place at 50 astronomical units is not a physical edge. It is a detection horizon, a limit of current observational capability, beyond which structure continues to exist, but remains invisible to surveys that have not yet achieved sufficient sensitivity to reveal it. The Kuiper Belt does not end. It continues, thinning gradually rather than stopping sharply, extending the Sun's structured outer domain far beyond the region currently mapped. A second belt means the solar system's outer architecture is more complex than anyone anticipated, not just larger, but layered. A distinct outer ring of icy bodies, separated from the classical belt by a gap in the radial distribution, would represent an entirely new class of solar system structure with its own formation history, its own dynamical evolution, and its own scientific implications that no existing model has yet addressed. It would require a significant revision not just of the Kuiper Belt's extent, but of the theoretical framework describing how the outer solar system assembled itself and what processes have shaped it over 4.5 billion years. Alan Stern, New Horizons principal investigator, described the finding as potentially representing the first time a spacecraft had discovered a new population of solar system bodies through in situ measurement rather than through telescopic observation. The careful phrasing matters. Dust measurements alone cannot definitively identify the source population. The instrument records impacts and particle sizes. It does not record return addresses. Every dust grain that strikes the detector carries no label identifying whether it originated from an extended classical belt or from a physically separate outer structure. Distinguishing between the two interpretations requires complementary data, either direct detection of the postulated outer objects by telescopic surveys, or additional spacecraft measurements that can constrain the spatial distribution of dust production more precisely. As of early 2026, no ground-based survey has yet confirmed the existence of large objects in the region where New Horizons detected anomalous dust levels. But the surveys sensitive enough to find them are only now coming online. Set this finding aside for a moment and consider a separate piece of evidence pointing toward hidden structure in the outer solar system. For years, astronomers studying the orbits of a specific subset of distant Kuiper Belt objects bodies on highly elongated paths that carry them to distances of several hundred astronomical units at their farthest points, have noticed something unusual about their orbital orientations. These objects, sometimes called extreme trans-Neptunian objects, do not have randomly distributed orbital parameters the way you would expect if they had simply been scattered outward by Neptune and left to drift independently. Their orbital planes and orientations cluster together in ways that statistical analysis suggests are difficult to explain by chance. The probability that this clustering arose randomly, without any external gravitational influence organizing the orbits, has been estimated at roughly 1 in a few hundred to 1 in a few thousand, depending on the specific data set and the statistical method applied. These are not overwhelming odds, they are suggestive rather than conclusive. But the pattern has been consistent enough and persistent enough across different surveys and data sets to motivate a serious scientific hypothesis. In 2016, Konstantin Batygin and Mike Brown at the California Institute of Technology proposed that the orbital clustering could be explained by the gravitational influence of an unseen planet orbiting at several hundred astronomical units from the Sun on a highly elongated path tilted relative to the plane of the known solar system. This hypothetical body, referred to informally as Planet 9, would need to be roughly 5 to 10 times the mass of Earth to produce the observed clustering through its gravitational shepherding effect on the distant Kuiper Belt population. At several hundred astronomical units, such a planet would be extraordinarily faint, reflecting only the most feeble trace of sunlight back toward Earth, making it invisible to surveys that were not specifically designed to search for it. The hypothesis generated immediate and sustained controversy. Some researchers argued that the observed orbital clustering is a real dynamical signal requiring a gravitational explanation, and that a distant massive planet is the most parsimonious one. Others contended that the clustering is a statistical artifact, a false pattern produced by observational biases in how surveys detect faint, distant objects. Surveys preferentially find objects in certain parts of the sky, and at certain distances, the argument goes, and if you account for those biases properly, the apparent clustering weakens significantly or disappears entirely. In September of 2025, a new analysis published in the monthly notices of the Royal Astronomical Society proposed a variant of the hypothesis with a different set of parameters. Based on orbital clustering detected in a new dataset of distant trans-Neptunian objects, the study's authors suggested that an unseen body at least 25 times the mass of Pluto might reside within a few hundred astronomical units of the Sun, closer than earlier Planet 9 estimates. The study could not determine whether this body was a large Kuiper Belt object, a sub-Neptune-sized planet, or something in between. It identified an anomaly in the orbital data and proposed a gravitational explanation. The confirmation of that explanation awaits direct detection. No telescope has yet found Planet 9. Dedicated searches using the Subaru telescope in Hawaii, the Canada-France-Hawaii telescope, and space-based observatories have surveyed significant fractions of the sky to the faint magnitudes where such an object should appear if it exists in the regions most models predict. So far, nothing has been found. This absence is informative, but not conclusive. The parameter space of possible orbits is enormous. A single object on a highly elongated path tilted significantly relative to the ecliptic could be anywhere in a huge volume of sky at any given moment, spending much of its orbit in regions of sky that surveys have not yet covered to sufficient depth. The Vera Rubin Observatory, when its full legacy survey of space and time reaches its operational stride, will either find Planet 9 or rule out its existence across a significant fraction of the parameter space that current models consider most likely. The answer, one way or the other, will arrive within the next decade. The Planet 9 debate illustrates a broader truth about the Kuiper Belt that the dust anomaly and the orbital clustering together reinforce. Despite 3 decades of systematic survey work and one of the most technically ambitious spacecraft missions in the history of planetary exploration, the outer solar system remains fundamentally incomplete as a mapped and understood structure. Its population is undersampled. Its outer boundaries are unknown. Its largest members may not yet have been discovered. Its dynamical history, while broadly understood, contains unresolved chapters that new data continue to complicate rather than clarify. The Kuiper Belt is not a solved problem. It is an active frontier, and the evidence for this does not come only from spacecraft dust detectors and orbital statistics. It comes from observations of individual objects that continue to produce results that existing models cannot explain. In May of 2026, a team of Japanese astronomers led by Koichiro Arimatsu of the National Astronomical Observatory of Japan announced a discovery that the scientific community received with a combination of fascination and disbelief. During a stellar occultation event observed from multiple sites across Japan in January of 2024, a Kuiper Belt object designated 612533, also known by its provisional designation 2002 XV93, passed directly in front of a distant background star. When an airless body passes in front of a star, the star's light cuts off sharply as the object's edge crosses the line of sight and returns just as sharply when the object moves past. The transition is essentially instantaneous, limited only by the finite size of the star's disk and the diffraction of light around the object's edge. It is the astronomical equivalent of a clean knife cut across the light beam. The occultation curve recorded from Japan on that January night was not sharp. It was gradual. The starlight dimmed slowly before the main occultation event and brightened slowly afterward, in a pattern recognizable to anyone who has studied planetary atmospheres. This smoothed profile is the signature of an atmosphere, a tenuous envelope of gas surrounding the object and bending, scattering, and absorbing the background star's light as the object's limb crosses the line of sight. The finding, published in Nature Astronomy, was startling for reasons that go beyond the simple detection of an unexpected atmosphere. The object is roughly 500 kilometers in diameter. At that size, its surface gravity is so weak that gas molecules with any significant thermal velocity should escape to space on timescales far shorter than the age of the solar system. For a permanent atmosphere to persist around such a small object at these temperatures, the gas would need to be continuously replenished, from the surface or subsurface, at a rate sufficient to compensate for the constant atmospheric loss. There is no obvious mechanism to sustain this. More puzzling still, earlier observations of this same object by the James Webb Space Telescope had failed to detect the surface volatile ices, methane, nitrogen, or carbon monoxide that would normally be expected on a body of this type and at this distance from the Sun. If the surface lacks these materials, the gas composing the detected atmosphere cannot be sublimating directly from exposed surface ice in response to whatever feeble solar radiation reaches 40 astronomical units. It must be sourced from somewhere below the surface. Two hypotheses have emerged to explain what the occultation data recorded. The first invokes cryovolcanism. The object may retain enough residual internal heat from radioactive decay in its rocky component to drive the occasional eruption of subsurface volatiles, releasing gas through vents or fractures in the surface, crust, and temporarily surrounding the body with a thin and transient atmospheric envelope. The second hypothesis involves a recent impact by another Kuiper Belt object. A collision large enough to excavate subsurface material and release trapped gases could produce a temporary atmosphere that might persist for thousands or tens of thousands of years before eventually escaping to space. On geological timescales, this would be a brief event. On the timescale of a single stellar occultation observation, it would appear indistinguishable from a permanent feature. Scott Shepard of the Carnegie Institution for Science, commenting on the discovery, noted that the finding demonstrates the Kuiper Belt is not a cold, dead collection of inert bodies, but a region that continues to harbor active processes and complex chemistry. The statement reflects a pattern that has been building for years across multiple lines of observation. Every time scientists look more carefully at the outer solar system, they find more activity, more complexity, and more surprises than the previous level of examination revealed. a 500-kilometer object should not have an atmosphere. The theoretical framework for atmospheric retention around small bodies at extreme heliocentric distances is clear and well established. And yet, the data from multiple independent observatories, recorded simultaneously from different geographic locations to eliminate instrumental artifacts, shows a gradual occultation profile that has no other credible explanation. The Kuiper Belt does not read the textbooks written about it. This is the pattern that emerges from every major line of inquiry into the outer solar system. Models predict a sharp outer boundary. The dust detector finds elevated readings past it. Models predict geologically dead worlds. New Horizons finds nitrogen glaciers and extensional tectonics. Models predict airless objects below a certain size threshold. A stellar occultation reveals a thin envelope of gas around a body far too small to hold one by conventional calculations. The outer solar system consistently exceeds the predictions made by inner solar system reasoning applied to outer solar system conditions. The reason, perhaps, is that the outer solar system is not simply a colder, emptier version of the inner solar system. It is a fundamentally different physical environment, where processes that are negligible or impossible in the warm, sunlit inner system become significant, where chemistry that requires billions of years of low-intensity irradiation to operate produces compounds that nothing in the inner system matches, where thermal budgets measured in fractions of a watt per square meter are sufficient over geological time to drive convection, tectonics, atmospheric cycling, and possibly the maintenance of liquid water beneath kilometers of frozen surface. The Kuiper Belt is not the inner solar system turned down to a low temperature. It is its own regime, operating by its own rules, producing its own surprises, and resisting every attempt to describe it entirely in terms developed for a warmer, brighter, more familiar environment. Against this background of persistent surprises and incomplete mapping, the Vera Rubin Observatory represents the most significant single advance in Kuiper Belt science since the discovery of 1992 QB1. Located on Cerro Pachón in Chile, at an altitude of approximately 2,662 meters, the observatory houses an 8.4-meter primary mirror coupled to a 3 billion pixel camera, the largest digital camera ever built for an astronomical facility. Beginning its full operational legacy survey of space and time in 2025, the observatory is expected to discover approximately 35,000 new Kuiper Belt objects over the course of its 10-year survey program. That number represents a nearly tenfold increase in the total known Kuiper Belt population. The implications of this data flood are difficult to overstate. With 35,000 new objects catalogued, the orbital distribution of the Kuiper Belt will be mapped with a statistical precision that current surveys cannot approach. The question of whether the orbital clustering that motivates the Planet 9 hypothesis is a real dynamical signal or an observational artifact will finally have sufficient data to answer definitively. The size distribution of Kuiper Belt objects, currently known only approximately because surveys are incomplete and biased toward the brightest and largest members, will be measured accurately enough to test formation models at the level of detail they require. New resonant populations, new dynamical families, new classes of objects that no current catalog contains will emerge from the data in numbers sufficient to characterize their properties statistically rather than anecdotally. The Vera Rubin Observatory will also address the question raised by New Horizons dust measurements. If a significant population of Kuiper Belt objects exists beyond 50 astronomical units, Rubin will find them. If the elevated dust signal reflects an extended classical belt, the objects producing that dust will appear in the survey data within the first few years of operation. If no such population appears despite Rubin's dramatically improved sensitivity, the second belt interpretation gains credibility by elimination. Either way, one of the Kuiper Belt's most pressing unresolved questions will move from speculation toward resolution. The James Webb Space Telescope adds another dimension to the upcoming revolution in outer solar system science. Its near-infrared and mid-infrared spectrographs can measure the surface compositions of Kuiper Belt objects with a precision and sensitivity that no previous space-based observatory could achieve. Surface ices that were previously detectable only on the largest and brightest objects are now measurable on smaller and fainter ones. Compositional gradients across the belt's different dynamical populations. The color and composition differences between cold classical, hot classical, and scattered disk objects can be characterized at a level of detail that transforms them from qualitative observations into quantitative tests of formation and evolution models. The convergence of New Horizons in situ measurements, the Vera Rubin Observatory's survey completeness, the James Webb Space Telescope's spectroscopic power, and ongoing ground-based occultation campaigns is creating a moment in Kuiper Belt science that researchers describe not as incremental progress along a well-understood trajectory, but as a genuine transformation. The belt is transitioning from a dimly perceived outer boundary into a fully characterized structural zone of the solar system with its own internal architecture, its own population dynamics, and its own active processes that continue to operate in ways that existing models are still struggling to describe. Every new finding reinforces the same conclusion. The Kuiper Belt is not what anyone expected it to be. Not when Jewett and Luo began their search in 1987. Not when the first objects were confirmed in 1992. Not when the NICE model described Neptune's migration in the early 2000s. Not when New Horizons flew past Pluto in 2015. At every stage of investigation, the outer solar system has revealed more complexity, more activity, and more structure than the previous stage of investigation had prepared scientists to find. And all of this, every discovery, every surprise, every revised model and unexpected measurement describes a place that remains almost entirely unvisited. A region of the solar system where one spacecraft has passed through on a trajectory it cannot alter, where ground-based surveys are only now beginning to reach the sensitivity needed to characterize the full population, where the most basic questions about extent and structure and activity remain open. The data tell you what is out there. The numbers quantify how far away it is. The images show you what surfaces look like under the feeble glow of a sun reduced to a point of light. What none of these measurements can fully convey is what it actually means to exist in that environment, not as a number in a dataset, not as a point in an orbital catalog, but as a physical reality. The weight of the cold, the depth of the dark, the absolute, annihilating completeness of the silence, and the emptiness and the distance. That reckoning is the part no instrument can measure, and it is the part that settles in last, after all the data have been absorbed and all the models have been updated and all the surprises have been catalogued and filed. It is the part that arrives quietly on a clear night, when you look up at the sky and try to hold in your mind the true scale of what lies beyond the last familiar landmark. It is the part that reminds you what the Kuiper Belt actually is. Not a dataset, not a diagram, not a collection of orbital parameters and surface composition measurements and theoretical models and spacecraft trajectories. A place. A real, physical place, part of your solar system, part of the same gravitational neighborhood where your world has been orbiting for 4.5 billion years. And a place so alien, so cold, so dark, and so incomprehensibly vast that confronting it honestly forces a reckoning with the true nature of everything you thought you understood about where you live. That reckoning begins now. -230 degrees Celsius. Write it down. Say it aloud. Let the number sit in your mind for a moment before moving past it, because the instinct when encountering figures this extreme is to acknowledge them briefly and continue, to let them register as large, and then file them away in the category of things that are technically true but practically irrelevant to any experience a human being will ever have. The instinct is to understand the number without feeling it. Resist that instinct. -230 degrees Celsius is not simply a very low temperature. It is a threshold beyond which the physical world becomes categorically different from anything human experience has ever encountered, or human intuition has ever been calibrated to process. It is not the cold of a winter morning, intensified. It is not the cold of a polar expedition, extended to a more extreme degree. It is a different kind of cold entirely, operating by different rules, producing different effects, inhabiting a different universe of physical possibility than anything the word cold normally implies. At -230 degrees Celsius, water ice does not behave like the ice in your freezer. It behaves like granite. Its crystalline structure is locked into a rigidity so complete that the material is mechanically indistinguishable from stone. You could quarry it, you could build with it. A mountain range constructed from water ice at these temperatures would stand for billions of years without deforming under its own weight, its peaks sharp and its slopes stable across timescales that dwarf the entire history of life on Earth. The mountain's New Horizons photographed rising 3 to 4 kilometers above the margins of Sputnik Planitia are not metaphorical mountains. They are real topographic features, structurally equivalent to any mountain range on your own planet, built from a material that would be liquid on any world closer to the Sun. At -230 degrees Celsius, methane is a pale crystalline solid. Nitrogen is a glassy translucent ice. Carbon monoxide, the gas produced by incomplete combustion in your car's engine, is a frost-coating hard surfaces in a thin layer of molecular stillness. Oxygen, if it were present in pure form, would be a pale blue liquid verging on solid. The air you breathe, the gas that fills your lungs with every inhalation, would fall from the sky as snow. At -230 degrees Celsius, chemical reactions that proceed in milliseconds at room temperature require millions of years to accomplish the same transformation. The molecular motion that drives every biological process, every enzyme reaction, every cellular respiration, every moment of consciousness you have ever experienced, slows to a vibration so faint that it carries no practical energy. Life is not merely difficult at this temperature. It is thermodynamically forbidden by the same physical laws that govern everything else in the universe. The machinery of biology requires thermal energy to operate. At -230 degrees Celsius, there is essentially none available. This temperature has persisted in the Kuiper Belt without interruption for over 4.5 billion years. Not for a season, not for an era, for the entire age of the solar system. From the moment the outer disk cooled after the sun's ignition, to the formation of the first bacteria on the young Earth, to the extinction of the dinosaurs, to the rise of every human civilization that has ever existed, to this moment, as you sit reading these words, the surface of a Kuiper Belt object has never once experienced a temperature that any living organism on Earth would recognize as anything other than instantly lethal. The cold is not a condition. It is the permanent, unvarying, absolute state of this region of space. It is what the Kuiper Belt is, at its most fundamental physical level. Everything else, the compositions, the orbital structures, the geological features, the moons and rings and contact binaries and possible subsurface oceans, all of it exists within a thermal context so extreme that the word extreme itself feels insufficient. Now add the darkness. The sunlight, reaching 40 astronomical units from the sun, carries approximately 1/1600th the energy it delivers at Earth's distance. At 50 astronomical units, the fraction drops to 1/2500th. These ratios are not expressions of dimness in the way that an overcast day is dim, or a candlelit room is dim, or even a moonless night far from city lights is dim. They describe a reduction in solar energy so severe that the sun itself, the nuclear furnace at the center of your solar system, has lost its authority as a source of warmth and illumination. Imagine standing on the surface of a Kuiper Belt object. You look up. The sky is black, not the dark blue black of a clear night sky on Earth, where the atmosphere scatters a faint background glow even in the absence of direct sunlight. Not the deep black of the stratosphere, where the atmosphere has thinned enough to show stars in their true brilliance. The absolute total vacuum black of a place where there is no atmosphere to scatter anything, no nearby surface to reflect anything, no source of diffuse illumination anywhere within billions of kilometers. Black. The way a sealed room with no light source is black. The kind of black that does not merely surround you but seems to press inward from every direction simultaneously. Against this black, the stars are extraordinary. Because there is no atmosphere to blur or scatter their light, every star in the sky is a perfect point of pure white radiance. The Milky Way blazes across the sky, with a clarity that no human being standing on the surface of Earth has ever seen. Its structure is not a soft smear of light, but a dense river of individual points stretching from horizon to horizon, the full complexity of the galactic disk, visible in detail, that even the darkest mountain sites on Earth cannot reveal. The sky is, in some purely visual sense, more magnificent than anything ever seen from the surface of your world, and somewhere in that magnificent sky is the sun. You can find it without difficulty. It is still the brightest single object in the sky by a wide margin, but it is not a disk. From 40 astronomical units, the sun's angular diameter has shrunk to approximately 48 arc-seconds, less than 1/40th of the apparent width it presents from Earth. Your eye cannot resolve it as anything but a point, a brilliant, sharp, unwavering point of light, surrounded by the fainter points of the stars, distinguished from them only by its superior luminosity. The object that dominates the sky of your home world, that fills roughly half a degree of arc from horizon to horizon, that warms exposed skin within seconds of contact, that drives every weather system and ocean current and biological cycle on your planet, that has served as the primary reference point of human timekeeping and calendar making and cosmological thinking for the entire history of your species, has been reduced to a star among stars. Brighter than the others, yes, but no longer a disk, no longer a presence, no longer yours. This transformation is not merely a visual fact. It is a psychological one, and understanding it requires recognizing how completely the human sense of place and orientation depends on the sun's apparent scale and warmth. You were born under a sun that fills the sky. Every sensory system you possess, every intuition about light and shadow and warmth and direction, was calibrated in an environment where the sun was close enough to cast sharp shadows, warm enough to heat your skin, large enough to mark the passage of hours by its arc across the visible sky. Your circadian rhythms respond to its light. Your emotional state responds to its presence or absence. Your concept of day and night, of seasons, of the year itself, is built entirely around the daily and annual rhythms of a nearby star. In the Kuiper Belt, that calibration becomes useless. The sun still rises and sets as the Kuiper Belt object rotates, but the event carries none of the meaning it carries on Earth. There is no warmth to welcome. There is no blue sky to accompany it. There is no gradual brightening of the horizon as the disk approaches. There is only a slightly brighter point of light crossing the sky at the same pace as the stars surrounding it, indistinguishable in form from them, distinguished only by its greater brightness. Sunrise in the Kuiper Belt is a star becoming visible above the horizon, nothing more. The psychological weight of this reduction is something no data point can communicate. The sun is not merely an astronomical object to human consciousness. It is the anchor of lived experience, the reference against which all other experience is measured. Remove it, or reduce it to a point of light, among other points of light, and the entire framework of spatial orientation that human beings carry unconsciously through every moment of their lives dissolves. Out here, the anchor is gone. You are in your solar system, orbiting your star, connected to your world by the same gravity that holds the planets in their paths. And yet nothing about the environment reflects any of that connection in a way that human senses can register. You are here. The sun is there. Between you and the sun, and between you and every other object in this region of space, is a distance so vast that it has severed every sensory thread that normally ties a living creature to its environment. Consider what that distance means when it is translated into communication. When New Horizons completed its flyby of Pluto in July of 2015, the spacecraft was approximately 32 astronomical units from Earth. The signal confirming a successful encounter, traveling at the speed of light, the fastest any information can travel, took 4 hours and 25 minutes to arrive at mission control. By 2026, the spacecraft has traveled to roughly 64 astronomical units from Earth. A signal sent to it today will not arrive for over 8.5 hours. The reply, traveling back at the speed of light, will not reach Earth until 8.5 hours after that. Nearly 18 hours of total round-trip communication time for a single exchange. This is not a metaphor for distance. It is distance expressed in its most fundamental physical unit. The speed of light is not a technological limitation that future engineering will overcome. It is a law of physics. No signal of any kind, no communication of any nature, can travel faster than light through a vacuum. The 17-hour round-trip communication time between Earth and New Horizons in 2026 is not a temporary inconvenience awaiting a technical solution. It is the irreducible physical consequence of being that far from home. At Kuiper Belt distances, real-time communication with the inner solar system is physically impossible, not practically difficult, not technologically challenging. Impossible, in the same sense that exceeding the speed of light is impossible, because both are prohibited by the same fundamental physical law. Mission controllers sending a command to New Horizons do not receive confirmation until the following work shift. A question asked of Earth from the Kuiper Belt would not receive its answer until the following day. Each party is speaking into a void and waiting most of a day for the reply. The solar system is too large for conversation. For a spacecraft managed by a team of engineers and scientists who have anticipated this constraint and designed their systems accordingly, this delay is a manageable engineering challenge. But try to feel what it means from the other direction. Try to hold in your mind the physical reality of being in a place so distant that even light, crossing the solar system at 300,000 kilometers per second, requires most of a working day to carry a message home and return with an answer. You are not, in any meaningful sense, connected to your world anymore. You are part of the same gravitational system. You orbit the same star. But the distance between you and everything familiar has grown large enough that even the universe's fastest messenger cannot bridge it quickly enough to sustain anything resembling normal human interaction with the civilization that sent you there. Now extend that isolation inward, from the distance between the Kuiper Belt and the inner solar system to the distances between individual objects within the belt itself. The Kuiper Belt contains hundreds of thousands of objects larger than 100 kilometers in diameter. It may contain billions of smaller ones, spread across the full three-dimensional volume of the belt, from 30 to 50 astronomical units, and extending above and below the plane of the solar system. These objects are separated from each other by distances that make the solar system feel crowded by comparison. The average separation between large Kuiper Belt objects is measured in tens of millions of kilometers. The entire distance between Earth and Mars at their closest approach, the distance that defines the target for the most ambitious human space exploration programs currently under consideration, is roughly 54 million kilometers. That is approximately the gap between neighboring large Kuiper Belt objects, each one drifting through its own private expanse of nothing, separated from its nearest comparable companion by a void wide enough to swallow an inner planet's entire orbital radius. New Horizons had to be aimed with extraordinary precision, years in advance, to pass within 12,500 kilometers of Pluto, a target 2,300 kilometers across, and within 3,500 kilometers of Arakoth, a target 36 kilometers long. These were not casual navigational achievements. They required trajectory corrections of extraordinary accuracy, performed by burning tiny amounts of thruster propellant at precisely calculated moments, years before the encounter, to adjust the spacecraft's path by fractions of a degree across billions of kilometers of empty space. Miss the target by a small fraction of a degree at the point of launch, and you miss it by millions of kilometers at the point of arrival. The spacecraft threaded a needle across billions of miles of empty space to reach a single tiny body, drifting in a void where the nearest comparable object might be 50 million kilometers away. The precision required to do this is not impressive, because the technology is impressive, though it is. It is impressive because it reveals how overwhelming the emptiness of the Kuiper Belt actually is. You are aiming at objects so widely separated that missing one by the distance between Earth and Mars means you miss it entirely and travel for years through nothing before approaching anything else. This sparseness is one of the Kuiper Belt's most important and most persistently misrepresented physical characteristics. Every diagram showing the belt as a dense ring of closely packed objects, every artist's rendering depicting a spacecraft navigating through a crowded field of tumbling ice, is a lie of compression. The visual language of illustration requires that objects be shown close enough to each other to appear simultaneously in the frame. Reality offers no such convenience. The Kuiper Belt is overwhelmingly, almost incomprehensibly empty. If you stood on one Kuiper Belt object and looked in every direction with the most powerful telescope your civilization has ever built, you would not see another large Kuiper Belt object, not as a resolved body, not as a disk, not as anything other than, at best, a barely perceptible faint point shifting imperceptibly slowly against the background stars over hours of careful observation. Your nearest neighbor is there. You know it is there, because the mathematics of the belt's population tells you objects must exist in the surrounding space. But it is so far away and so faint at that distance that the most sensitive instruments ever constructed would struggle to reveal it. Compare this to the inner solar system, where planets are visible to the naked eye from each other's surfaces. Standing on Mars on a clear night, you can see Earth as a brilliant blue-white star. Jupiter blazes in the Martian sky as a point of light bright enough to cast a faint shadow. From Earth itself, Venus, Mars, Jupiter, and Saturn are visible without any instrument whatsoever, their distinct colors and steady light distinguishing them from the twinkling background stars. Ancient civilizations tracked these wandering lights across the sky and built entire cosmological systems around the patterns they observed. The inner solar system is populated enough, close enough, and bright enough that its structure announces itself to any attentive observer without requiring any technology beyond a patient eye and a clear night. In the Kuiper Belt, none of that is available. There are no naked eye neighbors. There is no bright wandering star to track across the seasons, no nearby moon to light the landscape at night, no evidence available to unaided senses that you exist within a structured system of orbiting bodies rather than floating in absolute interstellar isolation. Each Kuiper Belt object is an island, and between each island and every other island lies a darkness and a distance so complete that the concept of a neighborhood becomes not merely inadequate, but literally meaningless. You cannot have neighbors you cannot find. You cannot have a community separated from its members by distances that no living thing has ever crossed. The Kuiper Belt's objects share an address in the sense that they all orbit the same star within the same broad range of distances, but that shared address provides no more sense of connection than the fact that two ships in different ocean basins share the same planet. The address is mathematical, the isolation is physical, and in the physical universe, the physical reality is the one that matters. This is the threshold where the solar system stops feeling like a neighborhood and starts feeling like something else entirely. Something for which human language, built by and for creatures who have never left a single planet, does not yet have an adequate word. The inner solar system has a character. It has warmth, light, proximity, structure that announces itself without instruments, a scale comprehensible to beings whose entire evolutionary history was spent on a single world measuring 12,000 kilometers across. The outer solar system begins to dissolve that character past Jupiter. By Saturn, the Sun has shrunk enough and the distances between objects have grown large enough that the inner system's sense of place has begun to attenuate. By Uranus and Neptune, it has faded significantly, and at the Kuiper Belt, it disappears. Not gradually, not as a continuous fade that you might not notice if you arrived slowly. It disappears as a threshold, a boundary crossed between the last place that still registers on human senses as part of a structured, comprehensible environment, and the first place that registers as something fundamentally different, colder, darker, emptier, more absolute in its indifference to the existence of the small, warm organisms that happen to evolve on a rocky planet in the inner third of the Sun's gravitational domain. And the Kuiper Belt is not even the end of this dissolution. It is only the beginning. Beyond the belt and its associated scattered disk populations, the structure of the outer solar system continues to thin. The Oort cloud, inferred from the orbits of long-period comets that arrive from random directions on trajectories requiring millions of years to complete, stretches from roughly 2,000 astronomical units to perhaps 100,000 astronomical units from the Sun. If the Kuiper Belt is the porch of the solar system, the Oort cloud is the property line, a boundary so distant that it reaches a significant fraction of the way to the nearest neighboring star. New Horizons, traveling at 14 kilometers per second, the fastest any human-made object has ever moved through the solar system, has been traveling since 2006. As of 2026, it has covered 64 astronomical units. The inner edge of the Oort cloud begins at roughly 2,000 astronomical units. At its current speed, the spacecraft will not reach that boundary for approximately another 700 years. It will not reach the outer edge, estimated at 100,000 astronomical units, for approximately 30,000 years. 7 centuries to reach the beginning of the solar system's outermost structure, 30 millennia to cross it. The fastest object humanity has ever launched will spend 30,000 years crossing the outer solar system if it survives that long, which it will not, its power source long dead, its instruments silent, its transmitter cold. It will cross the Oort cloud as an inert piece of metal, no longer a spacecraft in any functional sense, just a small manufactured object drifting through the dark at 14 kilometers per second, carrying no information, performing no measurement, witnessed by no one. At that scale, the Kuiper Belt, vast as it is by any inner solar system standard, is merely the innermost fringe of the outer wilderness. It is the first step past the last familiar landmark, the beginning of a journey whose true extent reaches so far beyond any human timescale that it cannot be experienced, only calculated. This is the reckoning the Kuiper Belt forces on anyone willing to hold its true dimensions in mind without flinching. Not a single threat, not a dramatic discovery of something monstrous lurking in the outer dark, something quieter, and in some ways more unsettling than any monster could be. The solar system you thought you understood was a small bright room. Beyond it lies a cold, dark mansion whose walls you cannot see, whose dimensions you can only calculate, and whose true extent will not be crossed by any instrument your civilization has yet built within any time frame your civilization can meaningfully contemplate. The Kuiper Belt is where the room ends, and standing at that threshold, looking back at the warm, bright core of the planetary system that produced the only life known to exist in the universe, something shifts in how the whole picture looks. The 8 planets, the asteroid belt, the moons and rings and volcanic surfaces and magnetic fields and weather systems and oceans and atmospheres and biospheres, all of it compressed into the innermost 30 astronomical units of a gravitational domain stretching 100,000 times farther. A campfire burning in a wilderness so vast that the light of the fire does not illuminate the nearest tree. That campfire is everything you have ever known, every human being who has ever lived, every civilization that has ever risen and fallen, every scientific discovery, every work of art, every moment of consciousness in the entire history of your species happened within the circle of that fire's warmth. The Kuiper Belt is where the warmth runs out. Return for a moment to where this journey began, a place in your solar system where the temperature has not risen above negative 230 degrees Celsius in 4.5 billion years, a place where the sun has been reduced to a point of light, a place connected to your world by the same gravity, the same physics, the same unbroken chain of cause and effect, stretching back to the birth of everything. A place almost no one knows, not truly, not in any way that matches the reality. You know it now, and knowing it changes the picture, not the data, not the science, not the orbital parameters or the surface compositions or the theoretical models. The picture, the mental image you carry of the solar system you live in, the one that was handed to you in childhood and that has served, with modest revisions, as your working model of cosmic home ever since. That picture is different now, not wrong in what it contains, wrong in what it emits, wrong in its implied completeness, wrong in the quiet, persistent suggestion that the part you know is the whole. The whole is something else entirely. The Kuiper Belt begins at 30 astronomical units and extends to 50, to 100, to distances that blur into the theoretical outer populations associated with it. It contains hundreds of thousands of objects larger than 100 kilometers in diameter. It contains multiple worlds comparable in size to Earth's moon, worlds with geological histories, with nitrogen glaciers and water ice, mountains and tectonic fractures and organic atmospheric chemistry, and possibly liquid water hidden beneath frozen surfaces that have not changed temperature in 4 billion years. It contains contact binaries assembled gently from collapsing clouds of pebbles before the first bacterium divided on the young Earth, preserved in states of such extraordinary physical completeness that studying them is genuinely equivalent to reading the original record of how your solar system built itself from raw material. It contains all of this, in silence, in darkness, in cold, so absolute that the word absolute feels inadequate, in emptiness, so complete that neighboring objects are separated by distances wide enough to swallow the orbital radius of an inner planet, in isolation so thorough that even light, traveling at the universe's absolute speed limit, requires most of a working day to carry a message from the outermost explored reaches of the belt back to the civilization that discovered it. All of this is yours. It belongs to your solar system. It orbits your star. It formed from the same cloud of gas and dust that built the ground beneath your feet and the atmosphere above your head and the oceans that cover most of your world's surface. The Kuiper Belt is not alien territory. It is home territory that happens to be so large, so cold, and so unlike the small, warm corner of it where life arose that it registers on every human instinct as something categorically foreign. That dissonance is the most important thing the Kuiper Belt has to teach. Not the orbital mechanics, not the surface compositions, not the geological features or the atmospheric detections, or the contact binary formation mechanisms, or the anomalous dust readings from a student-built instrument on a spacecraft traveling at 14 kilometers per second through the outer darkness. All of that is remarkable. All of it deserves the careful attention that planetary scientists have devoted to it and will continue to devote to it for generations. But the deepest lesson is simpler and more personal than any of those technical details. The lesson is about context. Human civilization has spent its entire existence in the small bright room, the campfire circle, the warm inner third of the sun's gravitational domain, where solar energy is sufficient to maintain liquid water on planetary surfaces, where the distances between objects are short enough to create the impression of a populated neighborhood, where the sun is large and warm and present enough to anchor every experience of place and time and orientation that a living creature can have. Every human being who has ever lived was born in that room, lived in that room, and died in that room. Every story ever told, every question ever asked, every answer ever found, happened within the circle of that fire's warmth. The Kuiper Belt is the first place where the warmth runs out, the first structural zone of your solar system, where the sun is no longer a disk in the sky, no longer a source of meaningful heat, no longer the commanding presence that defines the difference between day and night, life and death, here and there. It is the threshold between the familiar and the absolute, between the place where the rules that govern living experience apply and the place where they do not. And here is what that threshold reveals when you stand at it and look back. The campfire is small, not small in any way that diminishes it, not small in the sense of insignificant or unimportant or unworthy of the attention and care that the creatures living within it have devoted to understanding it, small in the sense of bounded, finite, occupying a specific, measurable, surprisingly modest fraction of the total structure that contains it. The 8 planets, the asteroid belt, every moon and ring and volcanic surface, and magnetic field and ocean and atmosphere in the inner solar system, everything that human civilization has ever directly experienced or studied or sent machines to visit, fits within the innermost 30 astronomical units of a domain, stretching to 100,000. That is the campfire. That is the room. That is the entirety of everything your species has ever directly touched, or seen, or measured, or stood upon. Surrounding it, beginning just past Neptune and extending outward for distances that no instrument yet built will traverse within any human time frame, is the wilderness, cold, dark, empty by any standard the inner solar system established as normal, populated by worlds that will not be visited in your lifetime or your children's lifetimes or their children's lifetimes, holding answers to questions about the solar system's formation that cannot be obtained any other way, preserving, in 4.5 billion-year-old frozen silence, the original materials of planetary construction that every geological and thermal process in the inner system has long since erased. The wilderness is not hostile to you in the way that a predator is hostile, or a disease is hostile, or even a storm is hostile. It is indifferent. It does not know you exist. It does not know anything exists. It is simply cold and dark and empty, operating by the same physical laws that govern the warm, bright room you came from, producing the same mathematical elegance of orbital mechanics and gravitational resonance and thermodynamic equilibrium, doing all of this with complete and total indifference to the question of whether any consciousness has ever arisen anywhere within it to notice. The indifference is not a flaw. It is the nature of a universe that was not built for any particular outcome, that does not favor warmth over cold or light over dark or life over lifelessness. The universe contains all of these things in the proportions that physics and chemistry and the laws governing the behavior of matter and energy happen to produce. Warmth and light and life occupy a small fraction of those proportions. Cold and dark and emptiness occupy the overwhelming majority. The Kuiper Belt is not unusual. It is normal. It is what the universe looks like when you step outside the exceptional local conditions that happen to prevail in the inner solar system. It is what most of the solar system looks like. It is what most of every solar system probably looks like. A warm, bright core surrounded by an enormous frozen halo, the conditions for life occupying a small privileged zone, and the conditions of the Kuiper Belt extending across everything beyond it. This is not a reason for despair. It is, if you hold it correctly, a reason for something much closer to wonder. Because here is the other side of the perspective that the Kuiper Belt provides. The campfire is small, but it exists. In a universe that is overwhelmingly cold and dark and empty and indifferent, in a solar system whose dominant condition is -230 degrees Celsius and absolute vacuum and isolation so complete that neighboring objects cannot see each other across the void between them, there is a small region where things are different, where the proximity to a star is sufficient to maintain liquid water on a planetary surface, where the energy available to drive chemical reactions is sufficient to produce the extraordinary complexity of self-replicating molecules, where the conditions are exceptional enough and have persisted long enough that the matter of the solar nebula assembled itself into organisms capable of looking up at the night sky and asking where they came from and what lies beyond the last familiar landmark. That is what happened in the campfire, in the room, in the small, warm inner fraction of the sun's gravitational domain where you live. The Kuiper Belt makes the campfire look small, but the campfire also makes the Kuiper Belt look extraordinary by contrast, because the Kuiper Belt, for all its vastness and all its preserved scientific treasure and all its geological and chemical complexity, has produced nothing that knows it exists. It has produced worlds with glaciers and mountains and possible subsurface oceans and organic chemistry, conducted across billions of years by nothing but ultraviolet radiation acting on frozen methane. It has produced contact binaries and resonant populations and collisional families and ring systems that defy theoretical prediction. It has produced, in Arakoth, the most perfectly preserved record of the solar system's earliest formation processes that science has ever directly examined. But it has not produced anything that wonders about any of this. The wondering happened here, in the small warm room, on a planet orbiting at 1 astronomical unit from a star that, from 40 astronomical units away, appears as nothing but a bright point of light among the stars, on a world so small that it would vanish without a trace in any honest diagram of the full solar system drawn to scale. A world that exists in a region so cosmically privileged, so physically exceptional, so narrow in its range of conditions relative to the vast cold wilderness surrounding it, that the probability of its existence feels, when you genuinely reckon with the contrast, almost impossible to accept. And yet here it is. Here you are, The Kuiper Belt was discovered by two astronomers who refused to accept the empty space on the diagram as empty, who spent 5 years scanning the outer solar system night after night, year after year, finding nothing, and kept going anyway, who trusted the mathematics and the instinct and the patience more than they trusted the absence of evidence, and were rewarded on one August night in 1992 with a faint dot that moved. That dot has multiplied into thousands of catalogued objects. The thousands will become tens of thousands when the Vera Rubin Observatory reaches full operational capacity. The tens of thousands represent a fraction of the hundreds of millions that population models predict. The hundreds of millions occupy a volume of space that makes the entire inner solar system look like a pebble sitting in a stadium. The stadium is surrounded by the Oort cloud, stretching 100,000 astronomical units in every direction, its outer edge reaching a third of the way to the nearest neighboring star. This is the solar system, not the diagram, not the poster, not the row of 8 labeled planets arranged at roughly equal intervals with a tidy arc of white space where the solar wind meets interstellar space. The solar system is this: a small warm core of 8 planets and their moons and their rings and their atmospheres and their oceans, and on one of them, their life, surrounded by a frozen outer wilderness so vast that the fastest machines humanity has ever built would require 30,000 years to cross it, occupying a total volume that makes the warm inner core look like a candle flame burning in the middle of a continent of ice. The candle flame is all you have ever known. The continent of ice is almost entirely unexplored. New Horizons is out there now, in the dark beyond 64 astronomical units, traveling at 14 kilometers per second away from the sun and away from everything that made it and sent it and hoped it would survive the journey. Its power output has been declining for 20 years as its plutonium heat source gradually loses the radioactive energy that drives it. By the early 2030s, it may no longer have sufficient power to operate its science instruments. By the 2040s, it may go silent entirely, its transmitter too cold to generate a signal strong enough to cross the billions of kilometers back to Earth. And then it will continue outward, past the main belt, into the scattered disk, toward the inner edge of the Oort cloud, 700 years hence, a small manufactured object drifting through a darkness it cannot illuminate, carrying no information it can transmit, representing the furthest reach of a civilization that built it from the same atoms that the solar nebula deposited in the small, warm inner zone 4.5 billion years ago. It is, in its silent, outward drift, one of the most remarkable things your civilization has ever produced, not because of what it will do after it goes silent, which is nothing, but because of what it did while it was alive, because of what it saw and measured and transmitted back across the light hours, and because of what those measurements revealed about the place where it traveled and the place it came from. It showed you that Pluto is not dead, that the outer solar system is not empty, that the boundary at 50 astronomical units is not a wall but a horizon, and that beyond the horizon the structure continues, the dust persists, the surprises accumulate. It showed you that the solar system you thought you knew was the inside of a room, and that the room has walls you have never seen and a yard beyond the walls that stretches to distances you cannot walk across in any time frame your imagination can hold. It showed you the Kuiper Belt, and the Kuiper Belt in return shows you the campfire. From out there, from the cold and the dark and the emptiness of the outer solar system, the inner system does not look like a crowded neighborhood of 8 planets and their companions. It looks like a faint cluster of light in the darkness. A small concentration of warmth in a vast cold environment that extends in every direction without boundary, without end, without any feature that registers on living senses as anything other than the most complete and absolute absence of everything that living experience requires. That faint cluster of light is where you are. That warmth is where you were born, and where every living thing that has ever existed was born, and where everything that will ever be born in this solar system will be born. For as long as the sun burns, and the conditions that sustain liquid water on small rocky planets in the inner third of a star's gravitational domain continue to hold. The Kuiper Belt does not diminish that, it frames it. It provides the context without which the campfire's existence cannot be fully appreciated. You cannot understand how extraordinary the warm, bright room is until you have stood at its threshold and looked outward at the wilderness surrounding it. You cannot understand how unlikely the conditions for life are until you have measured the temperature that prevails across the overwhelming majority of your own solar system. You cannot understand how precious the campfire is until you have felt, even in imagination, what the darkness beyond it is like. -230 degrees Celsius, 4.5 billion years of unbroken cold, hundreds of thousands of worlds drifting in silence so complete and isolation so absolute that the concept of a neighborhood has no meaning there. The sun reduced to a point of light. The warmth reduced to a memory of a star too distant to feel. That is the Kuiper Belt. That is your solar system's outer wilderness. That is the true scale and character of the cosmic neighborhood you have always lived in without knowing its full extent. And here, in the small warm room, in the campfire circle, on the pale blue dot, orbiting 1 astronomical unit from a star that blazes across the full half-degree width of a sky filled with breathable air and liquid oceans and 4.5 billion years of accumulated biological complexity, something happened that has not been confirmed to happen anywhere else in the observable universe. Matter became aware of itself. Atoms assembled from the solar nebula, preserved in the same cloud of gas and dust that produced the frozen objects drifting through the Kuiper Belt 4.5 billion kilometers away, organized themselves over billions of years into structures capable of asking where they came from, of looking outward past the campfire into the darkness and asking what is out there, of building instruments sensitive enough to detect a slowly drifting point of light in the outer solar system and recognizing it as a new class of object, of launching a spacecraft the size of a piano across 5 billion kilometers to look at a frozen world in a wilderness too cold for any biological process to function, of measuring and understanding and wondering. The Kuiper Belt is indifferent to all of this. It was drifting in the same cold darkness before the first cell divided on the young Earth, and it will be drifting in the same cold darkness long after the last organism on the last warm world in this solar system has ceased to function. Its objects do not know they are being studied. Its dust does not know it is being counted. Its contact binaries do not know they are being photographed and modeled and cited in papers published in journals on a small rocky planet 9.5 years travel away. But you know that the solar system does not end at Neptune. You know that the Kuiper Belt is not empty space, but a frozen wilderness larger than the entire planetary zone, populated by worlds that preserve the solar system's earliest formation records in conditions of extraordinary physical permanence. You know that Pluto has nitrogen glaciers and water ice mountains and a possible hidden ocean and an atmosphere that breathes in and out over centuries. You know that Arakoth was assembled gently from a collapsing cloud of pebbles 4.5 billion years ago and has not changed since. You know that the border at 50 astronomical units may not be a border at all, and that beyond it the structure continues into regions that no instrument has yet characterized and no spacecraft has yet crossed. You know all of this because someone, somewhere, looked at the white space at the edge of the diagram and refused to believe it was empty. The campfire burns in the dark. It always has. It is small and warm and temporary and surrounded on every side by a cold that does not know it exists, but it burns. It has been burning for 4.5 billion years. And in the last fraction of a second of that 4.5 billion year history, something in the campfire began to notice the dark, began to measure it, began to understand it, began to send small metal objects into it at 14 kilometers per second and listen across the light hours for what they had to say. The warmth is here, on this world, in this moment, in every instrument ever built to look outward, and every mind that has ever asked what lies beyond the last familiar landmark, and every answer that has come back from the darkness to say that the solar system is larger than you thought, and stranger, and colder, and more complex, and more indifferent, and more full of preserved wonder than anyone standing in the warm, bright room had reason to expect. It is extraordinary, it is temporary, and it is us.